programmer. So in effect, you can get some nice syntax. So that's OCaml, for example, right? We can get some nice direct syntax where we just call a series of functions or a series of methods which actually have some side effects, and their results are available directly. This here is Unison, which also, I think that's an example with, yeah, some putting something in storage and raising exceptions. So we get this nice direct syntax. The continuations are there, they're just not available directly. You might know Alex, he's the author of Monix, and he often asks those good questions, let's say, on Twitter. Actually, this one prompted kind of this talk, so I'm very happy he does that. And he was asking if direct style, well, he wasn't asking, he was more like stating that direct style is in fact imperative programming. And we all know that imperative is bad. We should do functional, right? First of all, they are not exactly opposites, but let's say they are. But I wouldn't say, I'm not sure if I would convince Alex, but I would like to present an argument at least. And I would say that these two concepts are kind of orthogonal. You can do programming with monads in a purely functional style, but you can also do continuation passing style, so indirect style, using an imperative way, like futures, right, which are side effecting. So you can have indirect style, which is both purely functional and completely non-functional, right? And probably similar with direct style. You probably can't do pure functional programming in direct style, but you can still do a lot of functional programming with direct style, because direct style only says how we represent effects, and that we don't use monads, for example, to represent effects. It doesn't say anything about all the other characteristics that we've talked about. So the imperativeness, you have a lot of imperativeness in functional languages as well, right? The Haskell example over here, it's a sequence of steps that's very imperative. It's embedded in a functional language, but it's an imperative sequence of steps. Some people actually understand imperative as like doing global state, doing statements, and so on and so on. And once again, this does using direct style doesn't necessitate you to use mutable state, for example. So yeah, so direct style consequences. If we are doing direct style programming, we are probably using the language's built-in control flow constructs, so we don't have to use special versions of loops or ifs that are available for monads. We have direct execution, so we don't need the intermediate library level runtime like in Scala IO that's often embedded inside the VM or inside the language, and the effects are direct, they're not represented as values, which this last point here is kind of non-functional, right? But the others are fine. Okay, yeah, so that's just summing up what's direct style. That's how we defined it, just so that we can keep it for further reference. Okay, so how functional then is direct style? Let's try to quantify it a bit. So I would say direct style is as functional as possible, but without introducing I/O. Okay, so that's the last step that we don't want to do, because it would mean that we actually don't represent effectful computations directly. And this also probably means that we cannot do purely functional programming with direct style, right? There are some limited direct style options out there. So we've got that's Katz effect with async await, right? That's Zio with Zio direct, which allow you to do direct style in a limited way. It's limited because you cannot use high-order functions, for example, freely. You cannot, embed those .run or those .await calls anywhere. There's a limited number of places where you can use them. So a limited direct style is possible with the pure FP. But if we want to do direct style, pure functional programming probably is not going to be possible. So we have to live with that. But let's actually try to answer the question, how functional is it? And to do that, we will do a very subjective scoring of various approaches. it's totally invented by me. You might have a totally different score. But let's see how it goes. OK, so first let's see how Scala plus Katz effect would score, or plus IO, like Scala plus a purely functional effect system would score. So first of all, we have a category that's like provided by the language, right? We have functions as first-class values. That's, of course, possible in Scala. We have an expression-oriented language. Most things in Scala are expressions, not all of them, but most of them are. And we have a functional standard library that's also, I think, important when considering the functionality of an approach. Whether the standard library works with you or works against you. Okay? So these are like high scores. Then we have, you know, the other traits of functional programming that we have identified, right? Applying and composing functions, well, that's mostly the primary way you do, you write code when using Katz effect or IO. You mostly use immutable data. You probably don't do shared mutable state, and you probably represent effects as values. However, all of these are only based on discipline, right? It's not checked by the compiler. It's not mandated in any way, right? You probably do a lot of log.info in your, or maybe you don't, but many people do. Log.info in your purely functional code, and you know it's completely fine. The compiler won't say anything. Finally, we have a small category whether the behavior and data are actually separate. Scala is a hybrid language, so we actually can hide. You can actually combine these if you want to. OK, so now let's take a look at the direct style version. So these first three are unchanged, because that's just how Scala works. Now what about the rest? OK, so we still, in direct style, we still mostly work by applying and composing functions to a bit smaller degree, because effects are no longer represented as values. So if we want to operate on effects, we just use semicolons. If we want to sequence effects, we don't combine them into a description or anything like that. So the score is a bit lower. However, we mostly use immutable data structures as well. Right? That's just the way you do things in Scala. It's actually harder to do mutable data, I guess. We use a lot of algebraic data types, so case classes, sealed traits. We avoid shared mutable state just because it's good practice. This is also, of course, based on discipline, so the scores are a bit lower. We don't represent effects as values. Well, maybe we represent errors as either's, so there's like 2 points for that, at least. OK. But let's try to put it in a perspective as to how it compares to other approaches. OK. One note about pure functional programming and about this category of no shared mutable state, right? It's a very good practice to avoid, and it's great to actually avoid shared mutable state and not to make life harder than it is. But we will never actually escape it completely if we do pure functional programming or not. And that's because we have things like databases, HTTP, and so on. So, you know, if we have those two threads, the first thread writes to the database, you know, increases the age of a user. The second thread reads from the database. It's like a race. Like, you don't know what they will actually do. So however we represent those two functions, if they return IOs, if they use abilities, if they use capabilities, if they use immediate effects, as a programmer, you still have to think about the interaction more or less in the same way, right? The mutable shared state is there. It's maybe not as a global variable, because that would be just making life harder, but it is there, okay? But back to our functional scorecard, we will take a look at Java, just to see how it compares to direct style, okay? So, you know, Java is a language. You can represent functions as first-class values since some time ago. Most things are statements in Java, not expressions, so a lower score here. The standard library is completely non-functional, mutable data structures, so no help there. So here the scores are quite low. What about actually working with Java? You know, of course, you can use immutable data structures if you really want to, but the Java ecosystem doesn't, mostly, at least yet. You know, you have records, you can do ADTs, but most of what exists in Java is actually mutable. So you will probably end up using mutable data structures anyway. Same with shared mutable state. We don't really represent effects as values so the end score is quite low. So they try to introduce some functional things, like they call it data-oriented programming, which is functional programming just called differently. It's using ADTs mostly and separating data and behavior, but it's not really used widely in Java. And I don't think it ever will, like there's just too much Java history. So let's look at Kotlin, right? Kotlin is something in between Java and Scala. So it's much more expression-oriented. The standard library is slightly functional, let's say. For the collections, which are like the primary tool that we use every day, the collections are mutable. You often get read-only views of collections, but they are mutable inside. So, it's like 2 out of 5, let's say. We work with immutable data and ADTs more often. We still don't use effects as values, right? So, you can see that the score is somewhere in between Java and Scala. Also, let's look at Haskell, right? It should be our golden standard when it comes to functional programming. And indeed it is. It has top scores everywhere, except for, you can still cheat. There's actually no language out there which allows you to do purely functional programming end-to-end, right? Well, it allows you, but which mandates purely functional end-to-end. It might also be telling. You can always do unsafe perform IO in Haskell, somewhere deep in your function. Nobody will notice, maybe. So it's also not the top score, but close. And finally, let's take a look at another contender. Rust, I think, is surprisingly functional for at least, this metric might be completely broken, of course, or maybe Rust is a bit functional. But let's look at how it scores in our categories, right? Functions are as first-class values. It's there in the language. Most things are expressions. The standard library, you often work with mutable data because it's Rust, but it's quite functional in its flavor. Like we've got the higher order functions for working with collections and so on. So it's quite functional. We often work, well, we don't work with immutable data. We work with mutable data, but we do work with ADTs, right? We've got enums, we've got structs. So that's that's a concept that we know quite well. And we often use functions to actually operate on these data structures. So that's quite functional. We don't have shared mutable state because that's like the main feature of Rust, that you can't have shared mutable state. Of course, you can do unsafe still. There's an escape hatch, and we don't represent effects as values. So summing those up, we have our functionality score over here. So unsurprisingly, Java is on the low side. Haskell is on the high side over here. So the purely functional Scala approach is quite high, quite close to Haskell. But the direct style in our functionality scorecard isn't that far away, followed by Rust and Kotlin somewhere in between. Okay, so, that hopefully tries to answer the question, how functional is direct style? And you can say that it's pretty functional. So it's, as I said, it's probably as functional as you can get without introducing I/O, without introducing pure functional programming. So in a way, Scala is functional by construction, right? If we are using Scala, we have all those traits of a functional programming language. We have functions as first-class values, higher-order functions, it's expression-oriented, we have immutable data types. We just have to try not to spoil it. That's when we, try to advocate some approach as to how we should do programming in Scala. So we've got all those great tools, we just have try not to break it. And hopefully that's what we are doing in direct style. My interest in that evolved into a library. So you could say, that I'm trying to convince you that direct style is functional because I'm writing Ox, but it's actually the other way around. I'm writing Ox because I think direct style is quite functional, and because I think you can get a lot of value from functional programming just by using direct style, right? So in the Ox flavor, it provides some tools which aim to make it easier to actually work with direct style, like advocating using eithers for errors and exceptions for panics. So that's something similar to what you do in Rust. Of course, not using shared mutable state. If you, oh, that's twice. So we don't use shared mutable state. If you do need to, communicate some data between threads, you should use channels or flows, function composition, a prime tool for writing code. When you consider how much function programming should you do, it's always a question at which point a given approach, be it functional programming, be it object-oriented, doing very orthodox object-oriented probably isn't wise as well, right? So at which point does FP actually start providing the diminishing returns, right? If you can go purely functional, if your team loves it, that's great, you will get a lot of benefits. If not, there's still a lot that you can actually gain. In the casual variant, I think, still provides a lot of value. And functional programming in Scala is, by Scala's construction, is both ergonomic and practical, and it's supported by the language, by the standard library, and the community also works towards it. And you might also know Runar. He's the author of Functional Programming in Scala book. And there's like an interesting tweet from him. They're often interesting. They're often not so easy to digest and understand. But what he says is that he doesn't anymore, I guess, care about purity per se. What he's more interested in how compositional an approach is, right? So what this exactly means is a topic of another presentation. So maybe you can try to uncover that at some point. But there's also something to think about, I guess, how compositional our approaches are. Okay, so just before the end, I would like to mention my company, who is sponsoring a lot of Scala open source projects, such as Tapir, STTP, Ox, and others, and Magnolia, although we will have to fix Magnolia, as Mateusz pointed out yesterday. So what we do is we try to help our clients with various technical problems mostly. So clients come to us when they need some more capacity or specific expertise in the areas where we work. So like Scala, Java, Kotlin, Rust, TypeScript. So mostly type-safe languages, but also we do a lot of work with Kafka, with Java migrations, optimizing cloud costs, and so on. So if you would be interested in that, come talk to me. And that's all I had. I'm here for the rest of the day, so if you would like to discuss, what functional programming really is, I'd be happy to do that, or what direct style is. So I guess that's all I had, and thank you very much. I guess I'm right on time, so I'm not sure if we are doing some questions. Yeah, okay. So if you would have some questions, I can try answering.
Hi, thanks for the talk. So my question is regarding Ox, and specifically, how do you do inter-thread communication there, and especially, can you avoid mutability when communicating between threads?
Okay, well, no, you can't avoid mutability, of course, because the channel that is like the low-level primitive is a mutable. It's like a queue with extra capabilities, so it's mutable, but it's a thread-safe, mutable concurrent data structure. Yes, so that's one mutable thing that you need to use, actually. We try to kind of hide it, maybe, with a higher-level API. So there's like a flow API, which is lazily evaluated, and it uses channels underneath, but sometimes you do need to get to a lower level and actually use the immutable data structure.
Another question. What's your take on the effect tracking? So we don't necessarily need to wrap in direct style, but what's your take on seeing the effects in signatures one way or another?
Yeah, okay. So we actually tried that in Ox to track effects. We tried to have an IO marker which would tell you in the signature that this method might actually do some I/O. So it sounds like a good idea, right? To have signatures that don't lie, and to be able to, predict if this method is going to take longer or shorter, or to know what kind of failure modes a specific method might have. But in practice, it turned out to be a burden, and you just had to put the I/O everywhere anyway. So in the end, we removed it. I'm not 100% sure if it's a good decision. However, I think the lesson here is that just having a marker trait which doesn't do anything, right? It was there only on the compilation, during compilation time. It never really did anything at runtime. It wasn't needed at runtime. It's usually just not worth it. If it's like a byproduct of actually having some runtime characteristic, then okay, great. But just for the sake of tracking effects, it turns out in practice it's more of a burden than benefit. And usually, if you have even the naming of the method kind of reveals if there might be side effects or not. So that's often duplicating information in that way.
One last question? No?
Nice talk, thank you. I'm curious, when writing applications, have you noticed any issues with a lack of referential transparency in functions? Has the side effects caused issues that were sort of unforeseen?
Okay, so referential transparency is something I left out on purpose because actually I have issues with it. It's not that easy to define. I know the common definition that you can replace expressions with values, right? But then, you have to ask yourself, what's a value? Because what is actually a value is like a value lives in a different world than the syntactical text of the program that you have, right? So if you actually go into program semantics, like the notational semantics, operational semantics, you often get that the value of a program includes the return value plus any side effects that it contains. So the definition itself of referential transparency is not that easy. But yeah, I kind of get the spirit of what it means, but I think it's more like a consequence of pure function programming. It's not like a benefit per se. I don't think you really often use referential transparency in your code. People often say that you can represent things as values, right? You can have a value which is represents a computation, and I would say in Scala you have vals and defs. You can just use a def if you want to have to have a computation, right? So to represent computations, we should simply use defs. That's the Scala answer, I guess.
Thank you.
Thank you very much.
Okay, great. Thank you. So have a good conference.
Okay, please welcome Dario Amorosi, who will speak us about optimizing data transfers from Kafka to BigQuery.
Okay, hello. Good morning, everyone. Thanks for attending. Yeah, I am Dario. Thanks for the introduction. Today we're gonna have a dive on a service that has been developed by my team 1 year ago, more or less, in which we optimized the transfer of data from Kafka to BigQuery in one of our pipelines. Before, I would like to have some word about my company. That's Adevinta. It's a global brand. Inside it, it comprehends a lot of marketplaces around the world. They mainly operates in the fields of the housing markets, in the automotive, and in the customer-to-customer sell of items. In French, the biggest one is Le Bon Coin. There are a lot of monthly users, around 120 million of active users, and this generates a lot of events in our pipelines that gives us a lot of nice use cases to solve, like the one that I'm going to present shortly. Some spoilers at the end of the talk, I will show how we saved roughly $40,000 per year with this new application developed, how we were quite happy with the solution. It scaled quite nicely. And also, we released the full code base in the Adevinta Kit. I will share at the end of the talk a QR code that you can use it to access. Maybe what you obtained can also be helpful to you. These are the points in which I will go through. First, I will introduce the problem. Then I will have an overview of the design of the service. Then we'll also go through a high-level overview of the CEO framework that has been used to develop the service. And then I'll wrap it up with the results. The presentation will be slightly shorter than the canonical 40 minutes, so I will take more or less 30 minutes for it. So everything started a few years ago. In my company, there was been a migration going on. Everything was on-premise, but there was the need to move in a cloud. So the pipeline was before exposing the data in real time on Kafka, and the data for the analyst, we had the HDFS in combination with Hive. In Google, the solution chosen for let the analyst explore the data was BigQuery. So since we were using the GCP cloud, my team had to build something to move the data in an optimal way. Dataflow is a service provided by Google. It allows to move data quite easily from one source to a destination, also applying some transformation. It's very nice because it's completely managed by Google. So my team didn't have to care about deploying the nodes. It provides out of the box some very useful metrics. There are some auto-scaling functionalities integrated. And so this has been actually implemented and worked for quite some time well. So what could go wrong with this solution? Well, after some time, the traffic ingested in our pipeline started to increase. And mainly, this made us more aware of the cost that this Dataflow job was rising. To give you an idea of the system, this pipeline was being ingested with data used for analytic purposes coming from all around the globe, from most of the marketplaces in Adevinta, roughly 2 billion of events per day, each of them being more or less 5 kilobytes. The main issues that we were having were that the Kafka cluster was composed by more than 200 topics, and Dataflow does not work very well with this many topics, at least in our experience. That's because we tried, to give you an idea, with one Dataflow jobs per topic, but this was not really clean. And also we tried with one single Dataflow job to consume and move the data, but this didn't start it up at all. Then we used one Dataflow job per marketplace. The Kafka topics were divided per marketplace, more or less 30 topics each. And the issue was that redeploying the jobs was taking a lot of time because the Dataflow jobs had to be drained and the new one had to be started. And it took 1 hour, more or less. That's not really the best if we want to experiment and do fast deployment. I mean, and also, yeah, the main reason indeed were the high cost. This was what made us more motivated to move away from this solution. So we decided this had to be redefined. This time we moved away by Google technologies and decided to use open source services instead. And also, instead of deploying it to Google, we deployed it through the company data platform that makes that easy for us to deploy the whole service. This is an overview of the application. It's composed by two services. The first one, the GCS writer, consumed from Kafka and writes on a staging area. That's Google Cloud Storage, the object storage of Google Cloud. And the second application is the BigQuery writers that reads the data in the staging area and issue the loading job in BigQuery. The whole thing has been branded Kafka BigQuery Express. Yes, it's a little long as a name, but you can find the service with this name in the Adevinta Git. This is an overview of the first service, the GCS writer. It's a Kafka consumer, so it starts consuming from all the topic and all the partitions. And deserialize the data, applies some light transformation, and serialize the data once again before writing them in Google Storage. The transformation that we apply are very lightweight. For example, we enhance the event with the date that will be later used as a partitioning key in BigQuery. And also, the service write the data in Google Cloud, adding some information, some metadata information in the file names. The most important here that I want to highlight is the end offset. So we don't commit offset to Kafka directly, but we manage the offset through the file names. This because if a file is closed and then the application restarts, then and it does not commit the offset to Kafka, what we will do is to create duplicates. In this way, instead, reading the offset directly on the closed file, we are sure that at least we avoid duplicates in this step. A closer look on how the file names look like. We have several information. We have the topics from which the events have been extracted, the table from which in which this will be loaded, the Kafka partition, always from the topic from which this has been consumed. Then we have the schema ID that will be used to serialize and deserialize the event, calling the schema registry. And then, we have two files. The first one is the .avro that contains actually the data. And then we have also a .don file. This is empty. It's just something that we save in Google to be sure that the counterpart .avro has been completely written and closed. This also contains the end offset. So we have both the first offset and the end offset for every file. These files are written for 5 minutes. This is to make sure that we don't have many small files in GCS. This is instead the second application, the BigQuery writer. What it does is to read the Google Cloud Storage staging area, and then it constructs the loading jobs to BigQuery. We try to do it in an efficient way. This means that all the files that can be loaded together are loaded together in a single loading jobs. The upper limit for BigQuery is around 10,000 files for a single loading jobs. And also we do this every 15 minutes. That's the minimum, so it means that the data in BigQuery are at least 15 minutes old. This is not an issue though, because these data are used for analytical purposes. And doing this more often faced us with issues in the quotas, because there is a limit on the number of daily loading jobs that can be issued to BigQuery. If we had one loading job every 5 minutes, we would have exceeded these quotas. Then, after the file are loaded, the BigQuery writer also cleans up the staging area. But doing this, we always make sure to leave the most recent DON file for every topic and every partition. This is because at startup, the file will be used indeed to start consuming from that particular offset for that topic and for that partition. This file can also be used if we, for example, want to do some maintenance operation and we want for one topic and one partition to start reading for one given offset. We can manually add one file in GCS and then the application will start reading from there. Okay. Then some word regarding the staging area. We implemented this solution using this staging area because we read some documentation regarding BigQuery, and one of the preferred way to load data in batch was indeed using a staging area in Google Cloud Storage. Once the data are there, Google will take care of loading the data in an efficient way. Also, if one loading job fails, we don't need to read the data once again. We still have them there. And yeah, it's also free as far as the data in the staging area are in the same region as the BigQuery dataset. Regarding the schema, we use Avro everywhere. In Kafka, we have Avro. In Google Cloud Storage, we have Avro. And in BigQuery, we load directly the Avro data. The schema is auto-detected by BigQuery. This helps us define the schema of the table without any additional task by our side. And this is good as far as all the evolution, all the eventual evolution of the schema are back compatible. That's our case. We evolve the schema quite often, but always in a back compatible way. And this means that we don't need to do any maintenance operation on BigQuery when this happens. Yep. Some small words also on how we deployed the thing. We use the Adevinta Common Platform. That's just a Kubernetes cluster with some quality of life improvements. And also the CI/CD is handled with Git Action in combination with Argo CD. We are quite happy with that also because it allows us for observability and how the configuration changes. It gives us some information regarding how the nodes behave after every deployment. So yeah, this was how we managed the deployment instead of relying on Google. Great. Now I would like to have a little overview on CO. The code of the service is completely used in CO. That is a library Scala for asynchronous concurrent programming. Most of you know about it. But I will go through the main advantages of using it. For example, that you can use it to wrap any JVM technology. The overheads that it adds to the Scala runtime is quite minimal. You can exploit with CO the full power of the Scala compiler. It provides very nice resources for avoiding leaking resources. And also, everything in CO runs with Fiber, that are how it allows for a high degree of concurrency. And also, I will describe briefly the Z-Stream, that how application, since our application heavily relies on them, everything is a stream in both the services before. So this is a simple example of a trait matrix that implements. It defines a function, Prometheus report. The return type of this method is a CO. We can see the CO type signature is composed by 3 classes. The first is the environment, that is what the function needs to execute. In this case, any doesn't need any dependency. Then we have the error type that the effect might throw. my favorite, I mean. It can be a custom exception, it can be a generic throwable, it can be nothing if it is a par function. And then in the end, we have the actual return type of the effect. This, and how can we wrap a service with a CEO? Is similar to how we operate in object-oriented programming. In the end, we are just programming two interfaces. So in the classic pattern to use a service with CEO, use three main building blocks. The first is just the trait that defines the functionality. The second is the implementation, here called metric live. Live is just a suffix that we add in CEO as a convention. In this case, we also have a member in metric live, that's metric dependency. This will be later passed by to when we instantiate this class. We implement also the Prometheus report function. All the logic is wrapped around a CO.attempt that will make the logic be executed over a fiber. And also will make the result being a CO. The third building block of constructing a CO service is a companion object for the implementation. This defines a layer. The layer can be seen as a builder pattern that defines how to instantiate the class. It can also be very useful because it can also be used to define how to clean up the resources of the class. Then what we do here is that we call the CO.service method to get the metric dependency implementation. So the caller where this layer will be called, also the implementation of metric dependency will be passed, and we will obtain that here automatically. And in the end, we will construct actually the metric live implementation, passing the dependencies. With this layer, we will obtain a zeta layer. That's how CEO will, how you provide an implementation to CEO. I will show this soon. Okay, this is the main class. This is the actual main class of the service without any further simplification. So it's quite minimal. What we do is first log the config, and then after that we start up a simple HTTP server that exposes the basic health check endpoints, the metrics endpoint, and concurrently we also define the message processor with the main logic that's defined inside the run method. Then we still need something here. It's not finished. Yeah, we need to inject there all the implementations, and you do it like this. So you provide all the layers previously defined. What you will do is to automatically resolve all the dependencies. If in a layer you need different implementation, if these are passed in the provide method, this will be actually obtained there. And also it will raise an error if a dependency is passed multiple times or it's missing. Yeah, regarding the fiber that are used to obtain the high degree of concurrency, this can be seen as an implementation of green threading, but also they can be thought as analog of Java threads that perform much better. One thing is that with just a few JVM threads, up to tens of thousands of fibers can run concurrently. That this is quite nice indeed. Also, fibers are very lightweight to create, and also yielding the execution from one fiber to another is a super fast operation. We remove almost all the preemptive scheduling overhead that we usually have with Java threads. Also, if Java threads are synchronous, fibers are by definition asynchronous. and also they are typed and composable. This means always with in relation to Java threads, there if you want to start a thread and run it, you will have to define a run method that returns void. So you can not really act on the return type of this run method. Instead, in CO, we saw that every CO has a return type. And so you can actually take the return type of a fiber and act on it in some way. Even if in my experience, I have to say this does not happen often. If I had to, I mean, in general, I never fork a fiber directly. I work on collection using CO utilities to work parallelly and concurrently on these collections. And CO will take care underneath to fork the fibers and wait for them. Some word on ZStream. Well, this is how, it's just an example in which, taken by the code, in which we list the files in GCS and transform them in a stream. Everything starts with the storage Google API. We list all the files present in the bucket in the staging area, and we get a stream with that. Then the ZStream from JavaStream allows us to convert the Java stream into a ZStream. What we do here is also to wrap the logic into a CO.attempt blocking. This is very useful because it allows us to execute this logic. That's an IO logic into a separate thread pool that is blocking. In this way, the other fibers running in the non-blocking thread pool are not disrupted at all by this. And yeah, in the end, we are just unwrapping the ZStream itself, because otherwise we would have a CO and the ZStream would be in the result. With the unwrap, we simply return directly the stream. And the caller of this function will be free to map over the stream and do whatever they want. Okay, so I wrap everything up. What we obtained in the end. Yeah, consistent cost reduction is the main advantage of the whole thingy. We saved roughly $40,000 per year. We scaled down in the data flow job. There were at most 13 nodes with 2 CPUs and 16 gigabytes of RAM. That, by the way, by the automatic auto-scaling capabilities of data flow, yes, it scaled up automatically, but after that, it didn't really scale it down, at least in our experience. So it was slightly problematic on this sense. We moved to our application that only runs in 4 nodes, each one of them with 3 CPUs and 16 gigabytes of RAM. Also, we improved the control that we had over the system. Now we had the occasion to, before we were relying maybe too much on the custom monitoring that Google provide, we took the occasion to improve it. We added a lot of better dashboards. We also manage the nodes by ourselves, so we have more control how the nodes are deployed. But most importantly, I would say that we reduced the deployment time drastically, because before we had to drain the data flow jobs and wait to start new ones. Now instead, with a few minutes, we can redeploy the whole service. Yeah, and in the end, we obtain a working application. It has been 1 year working quite fine. Hopefully, it will not fail tonight, and we are quite happy with that. Yes, I finished the slide earlier. Thank you a lot for your attention. You can find my LinkedIn, and you can also find the code. Please let me know if you are interested in it. You can find me. You can just send me a message.
Hello. Did you explore other solutions like Kafka Connect, like to push the data to Google Cloud Storage or any other solution of the market?
Yeah, the fact is that we had a very strong engineer that know a lot about SEO. We had some internal push. And also we had a similar application that was already loading the data on Google Cloud Storage. So we took inspiration from it. And since one of the preferred way to load data in BigQuery was to have the data on Google Cloud Storage, we went with this solution. We didn't explore it too deep, Kafka Connect and other alternatives.
Thank you.
Any other question? Okay, thank you very much.
universal et on n'a pas le droit de mettre les doigts dans la console.
Ok, donc
Ce qui est plutôt bien pour la vie à long terme de la salle.
je comprends très bien.
Pour nous, il leur impose des contraintes. Non, hélas, il n'y a pas. J'aimerais pouvoir, comme on a pu le faire au Palace, on avait même des serre-têtes et tout.
Ouais, bah en fait, voilà, moi c'était le truc. Quand on a un clicker et un micro, ça fait beaucoup de. J'aurais les mains très occupées. Mais
moi, l'autre jour, j'ai croisé un mec, un chasseur, il avait le fusil, le téléphone, les chandelles, pareil, un truc de trop.
c'est ça. Il y a tourné que de dos, donc ça devrait aller.
Oui, donc il n'y a pas d'arme chargée. Non, malheureusement, je suis désolé pour. Non, mais c'est.
Je demandais au cas où.
C'était une bonne question. Oui, voilà. Mais on vous entendra bien, c'est le son. Merci, à tout à l'heure.
Okay. So welcome everyone. Welcome to Plowing Postgres. First of all, before the beginning of the talk, I have two questions for you. So, who thinks you should never put your business logic in a database? So no one is raising hands, so I assume it's okay. And who thinks SQL doesn't compose? Okay, this is the two questions we're going to answer today. But first, we'll dive into a bit of a history because I like to introduce the tool I use. So what is Postgres? So we are back to 1970. There is some guy which is called EF Code. You might know already him. He's the guy who invented the relational algebra. And following its work at the IBM Research Laboratory, they beginning to program a system, a project to do relational algebra using data, which was called System R, which later became IBM DB2, if you have heard of it. And because the research lab was in San Jose in California and Berkeley was not that far away, some group of scientists at UC Berkeley began a project to implement also this relational algebra in a database they called Ingress. And side effect of this, they wrote a query language to manipulate set algebra, and this language was called Quell. So we're back to IBM, and the guy who wrote the system in IBM. So those two systems are quite coupled in terms of history. They needed a query language, but they didn't want it to use Quell. They wanted to use something better. They needed to do something better, so they made a SQL. And that's why SQL is called SQL, by the way. And also another funny fact about SQL is like at the beginning the acronym was SEQUEL, and actually it was already trademarked. So they got to find another trademark, so they removed the vowels and we got SQL. But it's just like a trick to being able to have their language trademarked. And by the way, there is some girls also at a company called Relational Incorporated, I think. They also began to make a database, a private one, and this company just became Oracle afterwards. So the history of like relational databases is very, very, very intertangled. So the Ingress project finished, and a scientist at UC Berkeley also, which is called Michael Stonebreaker. So who knows Michael Stonebreaker? Yeah, I know Olivier. Okay, but yeah, and they begin to make a sequel to Ingress. So they called it Postgres, and their query language was PostQuell actually. And their logo it was not an elephant actually, it was a turtle. And fun fact is, like in Japan, the Postgres logo linked to historical events when Postgres was open sourced, it's still a turtle. So the logo of Postgres is not the same in the whole world. So I begin the presentation with a lot of fun facts about Postgres, but don't worry, we'll get to see some more interesting stuff later. And finally, in 1996, we got the Postgres project as we know it. And they implemented SQL and not Quell, and so we got a PostgreSQL. That's it. So I wanted to do this presentation to present you how we use it and all use cases. So I work at Ledger. It's a hardware company, by the way, but we have a lot of backends, and basically we are indexing blockchain data to have better results and to answer better queries about it. And this is what I manage at Ledger. I manage indexing and transactional services. So, long story short, we got some old system which was using Cassandra because it was the trend at the time. There are big clusters, like three data centers with 8 Cassandra machine with a process that is analogous to ETL. So it was a lot of logic was in the Scala code actually, and not a lot in the database because Cassandra is a dumb database. It's not like personal. It's not very complex. What you can do with it. And we managed to migrate it to half the machine using Postgres. And we use more of a process. It's out of scope for this presentation, which is called ELT. So you extract, you load into Postgres, and then you transform it. And so you can use SQL to manipulate data, which is a good fit for it. And our motto for this project was to commit fully to Postgres, to make SQL a first-class citizen, to use it to manipulate data as much as we can, and to use all the features that SQL has to offer, because a lot of training, formation, and so on SQL focus on early SQL, like up to I know 1996 or something like this, and they don't introduce newer feature, and we'll see some cool feature in this presentation. And by the way, we are all doing it on premise, but with modern tooling, so we got to use an on-prem kube cluster, so it's possible. It's just that we need to know the tool you use. So if you don't delegate to a cloud company, you got to know it. And scaling vertically is very, very, very much viable. Like the use case, Google, on Facebook, on all the companies that use horizontal scaling is very niche, actually. And most of companies, you can just buy better machines, and it's wonderful. For instance, we got a lot of machine on OVH, and obviously, and this is what you can have for less than 800 euro per month, which is pretty hefty, and which should handle all your need for like the first year of your company. And if you can exceed this machine, that means you have a good problem to solve anyway. So that's it. And by the way, we use a bigger machine for production. Everything is possible. So, what is working with first-class SQL? So what we do here is like we try to use SQL as a language, so to add a lot of tooling and processes to make it scalable. Because a lot of services that I used in my experience don't use a lot of SQL. They wrap SQL as early as possible with very simple queries, and they compose then services between each other. And what we do at Ledger actually is to the totally inverse thing. Like we delegate a lot to SQL. So first, if you're gonna be serious with SQL, you got to have migration. You got to get your SQL code in your code base. So basically, we use Flyway. There is many tools in the market. But actually, we use Flyway for migration. Then we use Postgres schemas, so namespacing for version of tables. There is a lot of tricks using namespaces. I won't get into a lot of details voluntarily on this presentation, but you can version your schema and be clear about what version of the schema you use, and use views and transactions to make it clear. You need to schedule regular baselines also, because it's much more readable to have one big file that describes or create tables, for instance, and not having a lot of like 30 or 40 migrations that are one-liners. So maybe something that is very interesting is like you can concatenate all your migration file, and you get a much better picture than having it separated in your code base. And there is a debate about migration. Either you gotta go full independency or no independency. I mean, can your migration migrate twice and still get the same schema? I think it's a very bad idea actually, and that you should never use create if exist unless it is a very, very, very narrow use case. You got to do it, and yes, basically, you don't need it. Be confident. You don't need it. If the migration is not applied, it's not committed, and yeah. Okay, so once you have a schema, it's not enough. We need a lot of documentation. Today, it's documenting the code is a very big part of our job, actually. Either thinking about good names, thinking about architecture, and so on. So use it for SQL also. In your migration, you can comment in SQL with --, actually. You will see in the presentation. you can use the database actually to store comments. And there is in Postgres, you have the comment on any object, basically, is a string, and it will appear in tooling, in your IDE, in /d using anti/d using PostgreSQL. It's wonderful. Actually, you can store your comment in your database. I think it's wonderful, and it's also versioned into your schema, and you can add some like a lot of SQL wizardry. Is wizardry because it's not explained. Why does this guy make this query like this? So just use it. And then you got to test it because we're gonna write a lot of SQL. It's gonna be first class with complicated query, but actually you can test it a lot with your host programming language. Basically, test container is a no-brainer. I don't know who didn't know a test container, but if you don't know it for testing databases, go for it because it allows you to never use SQLite, H2, Derby, all these embedded databases again, because you're gonna use the core Postgres. It can also allow you to test new version of Postgres on your old code and validate migration and so on. And by the way, whatever is, if you take the SQL library you are going to use, they have a lot of modules helping for tests. For instance, Doobie has Doobie test. I won't show Doobie test, but actually you can check your queries against a live database, so you can factor a bit the thing between test container fixtures and having Doobie queries running, and so you can check every query you have in terms of encoder, decoding, encoding, decoding, and so on. In terms of just compatibility between JVM types and Postgres types, which are not 1-1. And you have Skunk also, and Skunk has a very nice feature that the error messages are the best error messages I've ever seen in my life. Come on, look at this. This is a good error message. Telling you what happened, how to solve it, where is the error. And this is what you can have. So you just have to run your queries in your test. You just have a test like this query must pass without throwing, and you get this nice feedback if you have any mappings and so on. By the way, I'm not taking any points in what library you should use. Just it needs to support like inline SQL because we are gonna write some SQL. And by the way, this is a very good usage of JSONB in our ELT process. Like we load a JSON and then we extract real data from this JSON to get the thing running. And then so insert is fast because you insert a batch of JSON lines, and the processing is very fast because you're only using the database against itself, and that's it. So when you are doing first-class SQL programming, I won't recommend having Quill or Slick or any type of code generation libraries because you're going to use a lot of feature of SQL, and SQL is made to be written and read also. And wrapping it to a Scala DSL doesn't defeat the purpose of what we are doing. We're going to try to quite never use fragment composition, because this is a plague for query performance, because you're gonna, if you, since we are functional programmer, we love equational reasoning, so we love to, I can factor this out, this subquery, it became a fragment, and then suddenly it's not a big subquery you manipulate, it's just a reference, a variable, and so you can use everywhere. So should you use everywhere? I think not, but we're gonna see a lot of ways to compose and to delegate and achieving the same conciseness without using fragment composition. And also, strict formatting helps. So, but I know it's very tricky because when you're going to use SQL queries, which are strings, into an interpolator, into a Scala code, it's hard to have the interpolated string having a different formatter than the host language. It's possible with, I think, my colleague Raphaël Lemaitre, if you that should be have presented in this conference. Just did it, so it's possible. It's not easy, but it's possible. And yeah, you will see we use a very opinionated formatting for a SQL. You like it or you like it not. What matters is like when whatever your team agrees on. So let's do it. And also a very important thing is like we gotta get out of the what I call the repository pattern. It's like you have, by the way, it's a modelization of RBAC, so role-based authentication. You have a user, you have roles, you have permissions. So user have roles, roles have permission, and so you need to authenticate people using this. And very naively, you will get this structure with a user repository, role repository, permission repository, and you get insert, update, get, and then you can compose these IOs on these methods to get what you want. And then you have more use case arriving, like things that are tackling end-end relationships. And this does not fit into the object model. Object model is made to have one relationship, one end relationship, end relationship doesn't fit well. You need to choose, either you add a role on a permission on a role. It's not clear enough, it's not satisfactory for me. So what I advise is better use some principle for CQRS. So we are not doing CQRS by the book with event sourcing and so on, but you segregate what is writing your queries and what is reading your queries. And often it's the separation you need, because the write path is often not the same workflow as the read path. And you can still compose this together because you can do transaction using it. And more importantly, since you're not anymore in a CRUD repository pattern, you can factorize your code. For instance, you can use these queries, which is more proper to your use case. Like, I want to add a bunch of user and roles, and that everything that's database just merge it with the current database. I don't need to see what happened. I don't need to check my case by myself. Just insert all the user with this role or with permission and so on and so on. So it's more about, this is a toy use case, I know, but the important thing is more about having queries tackling real use case, and to have to push away the frontier of what is handled by the database and what is handled by the code. So you can see that it's a bit like putting business logic in the database, but just by better separating things. And by the way, once you have queries, you need to iterate and optimize it, and having some feedback on how they are performing, because yes, you are writing SQL. SQL is a very particular programming language because you're gonna have execution plans. You don't have control on the algorithm you use. It's the database that chooses it for you, but you have some levers to influence it. So better be prepared. So usually we use a dedicated editor for SQL, like the Beaver data group module in IDE, or as I like, raw PSQL, because it's an awesome editor. By the way, you can edit files and so on in PSQL. There is a lot of tooling to do. And by the way, you can have a very much better explanation on your queries using all the options in Explain. It will be like bigger to read, but don't worry, I got you covered. There is a very nice website called explain.dalibo.com, and this thing is a very is a godsend when you want to I don't manage to do two things at the same time. Come on, no, it's how do I click a link on a Mac? So it's not my computer, by the way. But anyway, if you can help me. But anyway, this website, but what it does, it's like it allows you to take the execution plan, you copy it, you paste it, and you get a very nice graphical representation. Yes. So this is one of the queries we use, by the way. The execution plan, you can get it in the row tab. Sorry. No, it's okay. I will manage from this. You can get it in the row tab, so it's not a simple execution plan. You can see it. Anyway, full screen. F11? No. Go ahead. Okay, it's this thing, you cannot read it. It's not human readable, but on this representation, you can inspect it quite nicely. There are the bolder the links, the more row flow into your system, and you can using this, debug very big SQL queries. You have the time also. If you get all the options, as I told you, you get what buffer get hit by the query. If it does I/O, if you have there is bad estimates in terms of number of rows. If you have bad estimates all the way, it's maybe the time to do analyze on your table and wonderfully reduce your query time by 100. Yeah. But yes, and it's pretty big query. You can see you have a CTE, which is used 3 times actually, and you can rejoin the query also. Yes, please. Okay, so go ahead, try it. Very nice tooling, and it allows us to scale our SQL actually, because we can debug big queries. And then don't forget maintenance. I know the auto vacuum is enabled by default, but you can tune it. There is a lot of options, like depending on your read versus write ratio, you want to optimize it. I won't explain the whole vacuum documentation page. It will be pointless. But go ahead, go see the vacuum page of the Postgres documentations. You can tune it to your case. If you're interested into having no vacuum at all, there is one extension which is called OriolDB. At the time being, it's pretty, it's a bit mature, but it's pretty non-practical to use because you have to patch your Postgres instance and then install the extension. But I think most of the patches are already merged, and there is some that will be in Postgres 18, and afterwards we could just use it. But it's a storage engine that doesn't use vacuum. So if you have vacuum issue, you have a solution. Analyze is also run by the auto vacuum process, but don't forget when you have big migration of data, like transferring one table from one instance to another, analyze afterwards, because if you don't do it, query will be very bad. And then there is a third thing to do, which is very not known, a very niche use case, but very not known. As you may know, Postgres, when you insert data, it will create new pages and just append to these pages. So data layout on the disk is in the insertion order, which is not often the order you want to request data. If you want to order all your pages by, I don't know, one query index, you can do it using cluster. And actually, it will do a big I/O operation by rewriting all the pages in the order of the index you want to use. And so when you are scanning the index, when you are doing run queries, you are just pulling everything from the disk in a much less page fetch than the original order. So you may, if you are accustomed to Cassandra or NoSQL databases where you have a key value store and then you are ordered by key and you can scan very fast, it's Postgres answer to this. You can order rows in a cluster in a Postgres table. So I want to tackle this thing, which is SQL is a functional language. And that's why we love it using as a Scala user, because, by the way, that's why I love it as a Scala user, because it's very nice to use in this functional property. So first of all, what is a functional programming language? I won't get into the whole debate because I know it's very touchy. But actually, for me, it's using pure function as much as possible. We cannot be pure all the way because there is I/O to do. Even in a database, you cannot not do I/O. Let's get. And what is a pure function? Is a function which is well defined on its input domain and output domain, and which is deterministic. So obviously there is part of SQL that are not deterministic. Like if you ask to have no is like is not deterministic. Or if you want to generate a new UUID, it won't be deterministic. But let's be as deterministic as possible. So we can split SQL in many sub-languages. The two mains are like DQL, which is just select actually, data query language, retrieving data for the database, and you have DDL, which is data description language, and all the insert, update, delete. So you segregate what read the database, what write to the database. And once you do it, you can see it as a function like this. So DQL, you have some data that arrives to your program, and DDL, you have some data and you do effects. And actually, it's not that true, because as you may know, Postgres is like an ACID databases, so you have transactionability. And so what you are doing is always a consequence of being in a transaction. So if you write it with a transaction in mind, you get this thing. So you have a transaction, your transaction gets you a state of the database, and then you have a state of the database, read data. And this thing, and then when you are writing data, you have a transaction, you get a database state, then you have a function that takes data and write to the database. And actually, you will see, I have an example just afterwards, we can manipulate how a transaction is going to is flowing. So you can manipulate some sort of state encoding in a functional way using Postgres. So in terms of when you consider running the query, then yes, you are doing effects, you are getting data, you are putting data in the database. When you are in a transaction, things are much more functional oriented. For instance, here. Maybe you know it, maybe you don't know it, but you can do save points in a transaction. So you can save state at a point of the database and then roll back to this state. So you can have a dialogue between your code and the current transaction and really roll back to the point you want to roll back. And for me, actually, what I said a lot of things I won't, but you can disagree, and we'd like to discuss if you want. But for me, this is an accounting of the state pattern using SQL, by the way. But best to minimize this thing, one query per query. Try to achieve the most using one query is a bit of the leitmotif of this presentation. And then you need to have well-defined function to have and to have well-defined function. You need to constrain it as much as you can. From my previous talk, you see that I love constraints. so we'll see how to do it and how to push it to the maximum using SQL. You need to avoid abusable data type, for instance, JSON and arrays in tables. So JSON and arrays are very a good use case when you want to retrieve data, want to aggregate things. It's very useful. But when you are storing things, except if you have a very niche use case, like arbitrary data some user can put and so on, it's not that well behaved. And then you need to index it, and it became a mess. And third point is to build tool. I mean, relational databases, they exist for like 50, 60 years, and they are made to do joins. It's one of the most optimized things in Postgres is doing joins. It's complicated queries, but in terms of performance, building small tables, very narrow table with not a lot of columns but a lot of lines, and then you join them together, it tends to be, from my experience, a better way to achieve conciseness and have a good schema that scales. So well-defined. Let's check as much as we can to enforce constraints on your data. So you have the check constraints, which can arbitrarily check against an immutable constraints. Like you cannot check versus now or versus non-deterministic function. That's why I feel this functional programming vibes when I write SQL. It's like when you define a check or constraints, it needs to be deterministic. It needs to be immutable. Check can span multiple columns, by the way. You can check a column after at the table level and not at the column definition level. If you want to check not null, that something is not null, use not null. I think it's one of the most well-known constraints, but actually it's way faster than check A is not null. And because it's you have inlines and dedicated code path in Postgres to handle not null. And then a wonderful thing, which is you can create domains, so you can factor your constraints. If you are sick of having, like, for instance, you have an age in your database, you have many tables that use age, let's define it one way, put it into your migration, and never think about it again, because now you can declare a column which is of type age. And this goes for a lot of things. And the more if you want encode custom data types, you can do it using this. And by the way, this is much more powerful than the type system you have in Scala because you can check like arbitrary predicates and have to very narrow your type to what you want. So well, we covered checks. Then let's talk about consistency and how you can enforce consistency between tables. So first, you have unique index or unique constraints. You can just add unique to your column definition. You can also span many columns and have group of columns that must be unique in a table. And also it creates an index because it needs the index to check the constraints, and you get it for free. And yes, I won't get into much. I think it's very useful when you have generated IDs, but you have a natural key you want to enforce also. I don't know. I mean, the simpler thing is like you have an external ID from an external system. You need to couple it to your internal ID, so you get a unique column, and you get fast query from the external ID, which is often what you want, and still primary key enforced using Postgres. Okay, also you have foreign key. I think everyone also knows foreign constraints. What I wanted to stress is just like it does not create an index. So it can trick you into, this is efficient because I have like a foreign key relationship, but it's not at all. You need to create it afterwards. And it's often a good idea also when you want to work with data. And they also can span multiple columns. So if you have a primary key, which is a tuple, you can have a foreign key, which is also a tuple, which can be nice. And by the way, there is many options to handle deletion. Usually it's cascade in most systems, but there is many things you can set, like restrict to abort the transaction if the constraint is not satisfied. You can set null, you can set the default value, and so on. Speaking about primary key, actually, at the same thing, it's created index. It's one of the most well-known. The key can span multiple columns. So if you have a very nice pattern of column you need to have to query your data, put them all in the primary key. Same spirit as some NoSQL databases, but you can do it in Postgres. Actually, there is a custom type which creates a sequence. Everyone know it, which is big serial. But actually, it's not a SQL standard compliant, and Postgres encourages you to use a begin generated always as identity, which is actually the same thing. But one day maybe they will deprecate big serial, and everyone will be we need to upgrade. And yes, it uses an internal sequences. Sequences are like a mutable slot of data you can increase, and they are useful to handling sometimes, as you will see. Yes. Okay. Sorry. When you, just one funny fact, if you want to share a sequence between tables that share the same object, for instance, you have some types. You have a case for your data, and you want to create one table per case because you want to be efficient in your storage. So if you have this, you can create a sequence and then share it using it as a primary key of the other sub tables, and then having uniqueness cross table. If you want to check it further, you can use also foreign key relationship where it must be not joining against this key and triggers, but I won't get into it. Basically, the ultimate weapon is in Postgres is triggers, and there is very few use cases to use them, but I don't cover it into this presentation. And well, there is a constraint that is not very well known. You have something in Postgres which is called exclude. An exclude allows you to check against a collection type to ensure there is no overlap. Or than, for instance, a time period is before another time period, or some very range-y, array-y operation. And it's a generalization of unique, and it can span multiple columns. For instance, let's take this table. So we try to construct a maximum of this table. It's a bit of a summary of what we have seen. You have, for instance, resources and users, and they need to rent. Users need to rent resources for slot of times, and the slot of times cannot overlap for the same resources and the same user. So actually, what we can modelize thing, we can check that the start time is less than the end time at the table level and not at the column level. And then you can have an exclude using GIST, so it will use a GIST index. GIST is a method of indexing using most of the indices are B trees in Postgres, but you have many way to index data, and it's not covered by the talk. It could be a talk it could be a full talk actually on indexing, but you can using this method of indexing and matching resource with equal, user ID with equal, and then ensuring that the range of start to the end time does not overlap at the same time. So you can, this is code you won't have to check into your application anymore because you express it with 5 lines of codes in your database, and I find it wonderful. And then about abusable data types, it's not the normalization when you have performance problem is not a silver bullet and can bite you back quite hard. And keep in mind that it's also always a question of time versus size versus speed. If you inline a lot of things in your table, it will become slower. If you use better data structure, it can be faster, but it's always trade-off. And then use all the comment on tricks I show you to document it and enforce the documentation into the database schema to not confuse users. And about a bit of normalization, I explained it a bit when I told you about being tall. Joins are really fast, really fast. What is not fast is reading a lot of buffers from the page pool, which can be solved using a lot of techniques. For instance, cluster that I explained also. So then, let's compose this together. So SQL has a reputation of not being composable. Then people cannot compose SQL does not compose. For me, it's a bit of a rumor. And let's check together all the way you can use to compose a SQL within SQL. Let's take this query. So this query is a medium-sized query, which is not really satisfactory. You have two subselects. By the way, what you want to do, you have employees that have performance rating, and they have projects. And I want to see all the employees that have a good rating, but and involved in more than one project. So we got this into the code base, and this is not what we want. It's too complex. It's not readable, and it can trigger PTSD from a long-term SQL user when you see this kind of thing. Okay, so we have a lot of subselects. Where can we put subselect? And basically, the thing is everywhere. Actually, each clause that need a set of records, like from or where in, can have a subselect that can return many rows, but actually you can put a subselect that returns only one row in basically everywhere, in your where, in your join condition, in your select, and it can be, sometimes it's what you want to do, it's what you want to chain data, and but often it's very horrible to write because of SQL nature and enforcing of having the clause in the order they have. So let's take this query and let's use something we can, some tricks you can have. Is that we have the two subquery in blue and red, and what we are going to use is to use CTE. So who knows CTE? Okay, so it's pretty common modern knowledge. So CTEs allow us to factorize subqueries. So here I have a third one only to show that they compose together. So you can use old CTE to new CTE, and then suddenly you can read the code. It's in the order you want to present it. It's not the order it will be executed because you delegate it to a database. You release control. But anyway, you can have a much more readable experience using this. And by the way, some fun fact about CTEs. So you can extract logical subqueries. They can be recursive. It's out of the topic for this talk, but you can do graph processing using SQL and with recursive query. And they can produce memorization, which can be a good thing or a bad thing depending on what you want to achieve. But for instance, you can result, it's like the query I showed you in dalibo.com. You can reuse the result of a CTE in other CTE and then use memorization to reduce query time. But sometimes you want to enforce to just replace just copy and paste the subquery in place, and then you can use materialized or not materialized modifier in the after the CTE name. So you can enforce that a CTE is inlined using not materialized. And you can force that it is materialized, but I don't see the point of enforcing it. Okay, so sometimes you want to reuse it, cross queries. So what I advise here is to use views that are made to be, actually that are made to do it, to compose query itself. Sometimes we often use views to have an end table to fetch, but actually it can be used just to factorize things at the schema level. So here is the same query actually, and since it's just like a 10-line of SQL code, this is very readable, provided that you documented what is employee performance and project allocation, and cautious is views, so you can introduce subqueries and so on. And this is a part of what you need to introduce as comments. Okay, and by the way, you can, it's a very small thing, but I think some people doesn't know, you can order by tuple, which is very convenient when you want to have like a customizable ascending or descending order. You can just have your tuple and say, this two column in descending order. Yeah, so what I said, need to document it. You can do a very nice trick for schema updates using views, since you can separate the representation of your data from what is stored. So don't forget to use it when you do large migration. You can ensure that you have always a table which has a good name, which is queryable. Okay, so let's take back this thing and let's try to think more in a functional manner. This is not really what we want to do. Actually, we are composing two queries, but that are joining together, instead of having a query which is on a table and then joining after something. So let's refactor it this way. So what I did is just I choose a preferred way to query data. Like I take the responsibility to get first to the employee table with some filters. And then I said to the query optimizer, for each row of this select, just do a subselect. And this actually will be translated to a nested loop. And if you have a good join, a good schema with a good relationship in place, it will do the same as having these two subqueries with a join. Trust me, it's like I will use a nested loop join. And from this, you can see that there is a clear function, like you need to take a project ID and get the count, an employee ID, for instance, and get the count of project ID. So how can we reuse this piece of code? How can we factor it? The answer, we are doing we are all functional programmers. Let's do functions. And by the way, they are in your schema, they will be documented, they will be in your migration. So they exist, and you can factorize code using it. And actually, what I do is just, it's like one word. It's just I put a one-liner function. So one-liner, one query function. There is no logic. There is no full PLP, GSQL thing. It's just begin return query. It lacks a query. Your query end, and that's it. And then you have something you can use, which is typed, which can be documented. Actually, you can create a comment on this function, and you can use it this way. And if you need to share sub function in your code base, you can do it using this. We can still do better. What if I want to return not just a project count, but general statistics about my project? So I won't get in. I don't want to program a get project count, get project mean time, get project count for this category of project, and so on. I want to do it one for all and have it factorized. So how do I return many column from this kind of thing? And there is some neat tricks I wanted to show you using set returning function. Actually, a table in Postgres is a type. It's a product type. And it's very well known. It's the core of the relational algebra, having set of tuples. So you can return it. And we'll see two together. I just won't get in the slide running. Here's the function that returns a table. So it's maybe a bit hairy, so let's just discuss it together. You create a function, you have arguments, you have your project, your column, your table type, which is your return type, and then you begin a return query, and you do your query, the aggregation from employee project, where employee ID equal yada. Nice trick if you don't know it, you can use a filter in your aggregation, and this will fold in one pass. You won't get all the subqueries as you may have seen. You can just use filter like this. And using this, you will see I compute the statistics, and there you have project stats using employee ID. And then you wonder, how can we have this table run for each row? You need to have something called a lateral join, which can allow you to have join condition depending on like the set in the join can depend from the current row. And using this, it's like I can have side queries, like I can fetch data from other tables, do my .n relationships and so on, and get it back into my mains result set, maybe aggregating and so on. So here I can join lateral and having all my columns joined into this. Join lateral thingy on true is not very satisfactory, but thanks to Postgres you can factor it away, because what we want to do is a cross join between what we get and what the employee table. So you can write it like this, which is pretty neat. So you can use function to fetch data, and if you want to return tables, you can even fetch them, join them all the way, and your join condition or your join can depend on the current row. So what I wanted to explain is, maybe it's a bit difficult if you don't manipulate it a lot, but what I wanted to explain is like you have many tools to compose, and to compose it in a very beautiful way, because this is quite concise. Okay, and if you want, the only hard thing is like the lateral term. If you know what lateral things, like taking things aside and fetching them back, it's totally what we intend to do, like take this employee and fetch it project statistics. So you have many tools to compose in SQL. And reduce the noise for large queries. Some queries are still large, because by the way, if you want to do complex things, it's really complex to write, no magic. But if you want to do a very common thing, reuse part, have a more concise way, a more rationally thing to write, you can do it. You can put all your abstraction you create in your schema, like you put all your abstraction you create in your code. Let's play with your SQL schema. It's not like a religiously kept vault where you never move. It's something that can be dynamic. You can do migration and so on. And with good tooling, it's bearable. It's just that we are not used to use tooling for SQL. Tooling for a programming language is very well developed. You have LLM, you have a language server, you have a lot of things, completion, and so on. For SQL, it's not the same level, and it's a shame, I think. And then be relentlessly uncompromising with your queries. Like, don't be satisfied with quick and dirty work. Usually, when you write Scala code, you're not satisfied when it's not not perfect, but at least bearable for someone to read and so on. And I think a lot when I began writing SQL, like large queries, I was very dirty, and I put if it works, it works. And then you have just read-only code, and read-only code with SQL tricks and so on. It's not something you want to have in your company, because it's not something that scales. So that I wanted to say about SQL. By the way, this I want to do it because I think I don't have the time. But by the way, you can do your. It was just about having the 1-to-n relationships. If you have an article, you want to have all the comments for the article. You can do it in one query using a set returning function and a JSON BAG, for instance. And so you can fetch data and all the data, the side data in a JSON array. That's why JSON is very easy to. It's very interesting to use actually in Postgres because it allows you to have complex columns that came back to your application, and then to only do one fetch in database instead of two or n+1 if you're not cautious enough. So first, this is the opinionated part about what is a backend system. So when you modelize data, there is business logic because you have your domain model, you have your constraints, you put into your database. When you choose the data types, and you choose to put business logic into it. So you already have business logic in your database. Just a matter of where do you draw the line? Do you have a very dumb model, so it will be a very dumb representation of your domain model in the database? Or do you constrain it a lot and use functions, SQL functions and so on, to put a lot of work on the database side? It's some line you need to draw. It depends on your use case, actually. Sometimes a dumb model is better. Sometimes a very complex model is better. But anyway, if you choose to modelize things, you put business logic into it. Database is often, since cloud computing and since the introduction of ORM, it's seen as an external tool, and not a platform. It is a platform. Postgres is a platform. You can do a lot of things. Some people are building web server on Postgres. I won't recommend it, but you can do a lot of things. And it's a very powerful platform to manipulate data and tables and relational data. You have to reclaim it. And that's why Scala is very important for this to me, because it's the best lingua franca you can have to stitch things together between databases, external services, providers, and having a good HTTP interface or whatever you use. Scala is awesome because you can modelize things quite nicely. You can even put constraints into type. You can do a lot of type level stuff to ensure correctness and match the correctness of your database. So to me, we need to be aware that the software world is just databases that talk to each other, and using Scala is making glue between databases, and that's the message I wanted to show you today. Thank you. Are there any questions?
Thank you, Valentin.
Une
that's already like full macro all this stuff. So it's already up to this year. But there was a second year that landed February this year. I'll stop recording.
Et c'est bon?
En fait, tu peux démarrer avec un oh, c'est pas très grave si c'est en retard.
Comme ça, c'est bon, puis c'est bon, puis ça marche. Je ne touche plus à rien.
Ça, il y a le même problème.
Ouais, mais tu sais aller à côté de moi. C'est un câblage, tout ça.
Ouais, bah, mais non, mais de toute façon, c'est pas grave.
Et là, c'est bon.
Are you ready? Okay, this finally works. I'm glad that you had the patience to be here, even though we had some technical issues. So, my name is Alexis, and today I'm going to talk about something quite unusual, I will say, for conferences. Because even though that we are at 2024, I'm going to introduce you to Scala 277. Has anyone in the audience ever used the Scala 27 here? Come on. Really?
Not yet, no.
Okay, we had two guys, and it's more than expected, so that's good. To remind yourself, Scala 277, it's already 15 years old. It's ancient technology in the Scala world, which is only 20 years old, so this is 15. And it was also way, way different than Scala 3, or even Scala 213 is way, way too different. So we're going to talk about something that I got from a customer a while ago. I do a lot of contract work, freelancing gigs and that kind of stuff. And there was a time when someone came to me sharing that he needed to compile a very old application that happened to use Scala 277. This was last year, in 2023. So the whole idea is like, let's take this old project, help me to compile it, help me to build a fat jar, and make sure that it runs with JDK 8. Those were the requirements by this customer. The project I'm talking about is called Kestrel, one of those many projects that are at the Twitter graveyard. And even though this Kestrel project had like a more up-to-date version, the truth is that I was specifically asked to compile the branch that you see right there. And as you can see, it's marked like updated 13 years ago, but it was used like a README or something minor like that. So the presentation is all about what have I done in order to get this customer request succeed, and all the pain that I felt when I was doing that. So for every sane person that has worked with Scala, it's very likely that when you get into a Scala project, the first thing that you are going to do, look for the build.svt to see what I'm actually facing. What are the dependencies? Are there any external repositories? What are the configuration, the plugins, etc.? But wait, this project doesn't have one. There is no build.svt. For the few people that raised your hand, you might remember that back then, the project structure was different. build.svt didn't existed, and at the project, the build.properties file that you see here, where we tend to specify only the SVT version right now, back then, we could also specify the Scala version and a few other details like the one that you can see there. But anyway, what matters from this is that this is dependent on an ancient Scala and SVT version, SVT 073 and Scala 277. Then let's ignore everything else. There was also another build file that I was able to find called the Kestrel project.scala in an unusual location for what we are used to work with right now. And this is more similar to what we have saw at the build.svt. Here you see an external artifactory. We see also the library dependencies that the project has, the main class, and blah, blah, blah. That's basically it. That's how it looked, but we can map it to what we know. So what do we get from these initial insights? Well, first of all, you saw that there is no build.svt, but still we can derive what are the library dependencies. We can derive what Scala version, what SVT version should we use. And there was also another interesting thing. The SVT documentation for this ancient version is already is still alive. We can go and see the documentation. It was helpful. You might see later why, but it's helpful to know. And one hidden detail is that JDK6 is necessary for compiling this. And why? Well, because even though JDK6 is pretty old, with Scala 277 and SVT 073, it was released way before Java 6. Sorry, way before than Java 7. So we had to use Java 6. But the problem with Java 6, how do you get it? SDK man doesn't have it anymore. I have no idea why. But last year, at the end of 2023, you could just do SDK install and Java 6 something, and you could get the binary, and which is pretty nice. But right now, at 2024, because I tried this a few weeks ago, you cannot get it anymore from SDK man. So I went believing that Oracle, with that download page, might be able to help me. I had filled the registration form. I had agreed to receive the marketing emails from them, because otherwise they are not going to allow me to download the file. And once I do all of that, I get the not found error. So getting JDK itself is not a simple task, but I am not going to get into that right now. That's your own challenge. So what are we going to do? How are we going to proceed with this? There is a small trivia here. What do you think? Who believes that SVT is not going to launch if we try using the launcher from 2024? Who believes that it's going to refuse to launch just because the 073 is too old? No one. Well, that's good. I guess everyone else is thinking that SVT is going to load but generate a new project because there is no build.svt. Well, the truth is different, because SVT actually give it a try to download SVT 073, but the shell was not available anymore. So if you look, I'm not sure if you are able to read, but if you look, for example, it's trying to resolve this from Sonatype, from Maven Central, from the local repositories, but it couldn't find it. So there is no SVT there. Let's see what else we can do. Well, I managed to find this ancient SVT version and an old archive from Google Source something, where you can find all the jars for the SVT launcher. And for the ones that are new to Scala, we use it to call this a simple build tool, by the way. Simple. So I have downloaded the file, I have tried to launch SVT, and guess what? I got another problem. This time, it's complaining about something very similar, but the error message is slightly different. This is placing something that it's not able to resolve SVT 073 or Scala 277. Okay, the cursor is here. So the error is different. And we get a little bit more information as well. What you can see there is that there are a few more repositories that SBT is trying to fetch the data from. Not only Maven Central, not only Sonatype, there are a few other places. For example, this databinder.net, scalatools.org, and there are a few other places where these files used to be hosted. So what we can get from this is that many of the things that were alive before, they are not alive anymore. Does anyone remember the issue that we got a while ago related to Bintray, when Bintray was sunsetting? Anyone? Only a few? Lucky you. Well, we had the Bintray problem before. At least there are 2 repositories right there. And from the few of you who has been in the Scala ecosystem for a long time, you might notice that Maven Central right now requires HTTPS. But in the previous slide, you can see, where is? You can see that SBT was trying to reach to Maven Central through HTTP. If you try that, it's going to reject. So what does it mean? It means that SBT might be at Maven Central, but given that Maven Central refuses to attend this request, we don't really know, and we cannot do anything about it. So I'm not going to be able to find this SBT version because there are 2. One is the launcher, one is the shell. The launcher is there, but the shell is not there. So forget about it. What if we compile it instead? The source code is there. It took me a while to find it, but the source code is there. So what if we compile SBT 073? Well, I mean, I gave it a try. Why not? Well, let's look into the project, and it requires SBT 072. With Scala 277. So I was being paid to compile a Scala 277 application, which also requires me compiling SBT with 277. So what are we going to do there? The truth is that I actually give it a try. I started trying to compile the SBT shell. I'm not detailing all of this in the slides, but I did try it. And it got me to the rabbit hole because I had to compile JNA and a few other ancient libraries that I just couldn't actually deal with that. I was very annoyed. So let's just ignore all of that and forget about compiling SBT. So what can we do now? Idea number 1, we could upgrade the project to use a sane SBT version, something that we can actually download. And when I was reaching out to people at the Scala Discord, there were people helping me. It was said he's here in the audience. He doesn't remember, but he helped me. And he suggested, have you considered building a tool just for compiling this project yourself, resolving dependencies, mangling with the class path, etc., etc.? And that was a very good idea, which I actually considered. But at the time, I said, nah, that was too crazy. I don't want to build yet another build tool just for legacy projects. So let me try upgrade it to a sane SBT version. So let's drop away, let's take away everything from the build file that we have and just replace it by setting SBT 013 there. That's it, nothing more. And the only reason why I had picked up this version is because it can be resolved by SDK man. That's it. I didn't want it to bother with other stuff. So by doing that, SBT can launch. At least the shell is there, so there is some lag. But when I try to compile, the compilation will obviously fail, and this might be obvious for the Scala people that are already experienced with this kind of problems, because I never added the library dependencies, etc., and the configuration, which was simple. But another thing is that SBT was trying to use Scala 210, which will not actually compile. So if you see here, there at the top, I have updated the build.sbt. I had finally created one in order to specify that we need to use Scala 277. But guess what's going to happen then? Another not found error, because this cannot find a Scala 277. So by now, we had faced the problem resolving SBT. We couldn't actually fix it. Now we have the problem that the Scala 277 cannot be resolved. JLine, I don't care, that's a minimal thing. Then looking more into this, I find out that there is a way to let SVT pick a local Scala version, something that you have within your file system, which is pretty helpful. And also the Scala website has most of the versions from Scala from the past, and you can just download the tar file, extract it to your local, and you set it right there. So let me try that. What do you think is going to happen? Is it going to work? The audience is not very positive. Well, it does not, so right answer. But what the hell is this? I didn't know back then, I do not know right now. But what I can tell you is that after trying to find what the hell was going on, it seems that even though SVT 013 is pretty old, it's too new for Scala 277. They just cannot play together. So, what can we do now? Take the inverse path. Start downgrading SVT until we find something that can play with 277. That's one idea. Or the second idea is start looking more appealing by now. Perhaps I should build my custom build tool just for this. I got another idea. What about if I instead upgrade the Scala? Instead of 277, let's go up to see whether I might be able to get it to work with SVT. And that's what I'm going to pursue. I'm going to replace the build.svt. I'm going to change the Scala 277 by 282. And the reason for 282 is because that's like the next version from the Scala 277. I was going to try one, then the other one, then the other one, and to see what's going to actually fix the problem. But to my surprise, I was pretty lucky because we were this far to get the Scala resolved. With 282, I managed to launch SVT shell, and I managed to actually get this thing trying to compile the source code. So finally, something good in the whole presentation. So what's next? We get compile errors, of course, because we didn't have added any dependencies. So let's transform the other ancient build file into build.svt, defining the external repository, defining the dependencies, and let's see what's happened. What do you think? Is it going to work? Such a positivity here in the audience. Well, this is a not found again. You are pretty used to it and get used to it because this is not the last one. So there are many libraries that cannot be resolved. But pay a little bit of attention here. It says specs 2.8.2, something like that. Normally, you will see only like the underscore with 212, 211, or the 3, and that's it. But turns out that back then, with Scala 2.7, every minor version had binary incompatibility with every other minor version. So if you have something for Scala 2.7.6, it was not going to work with 2.7.7. So if you think that you have library problems right now, it's not that bad. Basically, this slide, it cannot work. So what should we do? Who thinks that we should do this? Anyway, so the other idea is maybe we can recompile everything to work for 282. Maybe if the dependencies are not that big, if there are not many transitive dependencies, maybe we can get that to work, or just do and follow the long path and compile everything manually. So looking a little bit into the dependencies, there are a few dependencies that are already there. Thank you, Java world. We hate Java, but sometimes Java is good. So the Java dependencies work, that's good. But the other 5 libraries from Twitter are gone. They do not work. So analyzing this a little bit more, I had to dig a little bit into many places, and I find that the source code is available for most of the libraries from Twitter. It's either in Maven Central, because when you publish a jar, you usually also publish the sources, unless you explicitly tell it not to. For some others, the source code is in GitHub. And for some others, it might be in an obscure place where you can actually find it. But importantly, the source code is there for most of the libraries. There are a few things like BS Scala doc that I don't care about because it's only documentation. My customer is asking me to compile the project, not to provide documentation. So I'm not going to worry about that one. So I'm going to drop the two libraries that seem to be unnecessary. The one for testing and the one for documentation. And let's focus only on the critical ones. And gladly there are only 3. That's a lucky day. So instead of compiling every of these libraries, resolving dependencies, running SVT publish local, or using my own Artifactory or publishing to Maven Central, instead of doing that, I can take a shortcut. I can copy the whole source code from each of those libraries and just put it within the project itself. That's it. That means that when I compile the actual project, the dependencies are going to be compiled as well. So no need to do publish local and that kind of things that takes time and it's annoying. So I'm going to try that. And this is what basically I did here. I felt pretty lucky at that time because the more critical library for the project was Twitter Actors, and apparently it was dependency free. So for library authors, try not to depend on too much dependencies because you might get an unlucky guy like me facing problems. So Twitter Actors, for the ones that are not familiar, basically Twitter had their own ecosystem back then. They had their own actors before Akka, before the Scala actors and everything. They had their own Scala futures, and basically this library is like part of that. So it's dependency free and that's good. Recompiling for sure is going to cause problems because I haven't added all the dependencies. Then I get to another library called Nagati. I have no idea what this actually does or what does it mean, but it's from Twitter, even though it's not at the Twitter namespace, it's from Twitter. And it has a few dependencies. But if you pay attention, these are the same dependencies that the main project is actually depending on. So that's another good thing, because if I manage to resolve those, I'm going to be able to compile this. So this is a lucky hour as well. Still errors, totally expected. Then the tier library, which is called config, no external dependencies, at least not obviously, still problems. Then turns out that the library that I actually ignored, it's necessary because they were using some kind of time class in order to be able to mock the time, what you can do with the Java clock right now. But remember, they were in Java 6. So I'm going to just copy this file. Like you can see here in the screenshot, I copy only the time. I don't care about anything else. I don't care about the test. I also removed all the tests for now. Then there are many compile errors, totally expected. And now this is the time that you were expecting for, trying to fix the compile errors. First of all, thank you to the IntelliJ plugin developers, because it's amazing that IntelliJ works with the Scala 282. And that has helped quite a lot in order to use the go-to definition, to look at the documentation instead of having to do it myself. And so thank you to the IntelliJ plugin developers. And let's look at the first problem. If you remember, I have copied the whole actor library from Twitter. Still, why is the actor class not being able to be resolved? What's going on there? That doesn't look right. Well, it turns out that one of the biggest changes from Scala 2.7 and Scala 2.8 is that the import resolution or the scoping was different. Right now, you know that if you have something within the package called Twitter Actors Scheduler, it means that you're importing everything from the scheduler package, but that's it. With Scala 2.7.7, it was different, and with Scala 2.7 in general. If you have something at the scheduler package, you were importing the actors, the Twitter, and the com. You were importing just everything. So after I fixed a lot of files that were having that by using this syntactic sugar in order to import everything from actors and from the actual scheduler package, I changed, I'm not sure, 50 files or something to just follow this convention, and 90% of the errors are fixed. Then, there are a few other things related to the collection API. There were many changes related to the collection usage between 2.7 and 2.8. There was this helper method to create an immutable collection based on a mutable one. The method didn't exist anymore. I'm not sure why. But we can pretty easily emulate that. We're just doing something like this. Okay, we need an immutable collection. Let's just convert it manually, and that's it. There were not so many places to do this, and that's another way to fix the problem. Then there were another signature changes that I had to change. For example, iterable to iterator, and it's also a relatively simple change like this. Like just replace the method signatures in order to fulfill the compiler, and that's it. But then we get into something a little bit more obscure. Apparently the iterable had something that the iterator does not, which are these two methods. And normally it would have been pretty tricky to get this right, but thank you to IntelliJ, I managed to find that we have an exist method and we can do the same thing that the contains does. But the other thing, this is the obscure one. How do we emulate the next from the iterator? I could have written this myself in a worse way, very likely. But turns out that the Twitter Actors library had a version that was cross-compiling to Scala 2.8 and to Scala 2.7. So I just went there and grabbed their source code and put it here. It made my job simpler because this was already tested. There was another problem related to the collection usage. If you pay a little bit of attention to the code that is here, I am not doing anything, really. I'm not doing anything, just rewriting the same thing into something more detailed. And this makes the compiler happy. And it works. We got the application compiling. For the one that we're expecting and resolve the dependency, it's not. It works. So now the time is prepare a fat jar. I managed to find that SVT assembly works for 282. So that was a wonderful surprise, because just adding those few lines, I managed to build the fat jar. Then in order to try it, I have to provide a few configuration, but that's not relevant to Scala. It's just configuration for the project itself. I run it like that. Then we get the logs. Just trust me, it's working. You need to understand what's going on, but it's working. And this is using Telnet in order to issue commands, and it's working. So if you want to do something for the Scala people, please keep your dependencies up to date. We have Scala stware, because it's pretty annoying to be dealing with these problems, especially when the artifactories are gone. We already saw the case for Vintre, we saw the case for the data binder, we saw the case for a Scala tool, something, and there are many places. And Scala compatibility between minor versions used to be very bad as well, so you are in a very good spot right now with Scala 3. Compatibility is way, way nicer than what it used to be. And if you ever had to do some kind of thing like compiling a legacy Scala application where dependencies are gone, consider pretty carefully what you are doing. Because, for example, when I went to the path of compiling SVT 072, it led nowhere, and you can waste a lot of time. And you can also try continuing to that path because you have already invested so much time into that and you don't want to actually skip and do something else. So consider carefully what you are doing, because this is annoying and it's not as simple as it should be. And that's basically, thank you.
Thank you for the talk. It's very entertaining. I'm a bit confused that it seemed like you had to compile a very specific branch, but then you changed the implementation and also compiled with Scala 2.8, so wouldn't it be incompatible with the original requirement, or did that not matter?
Well, the requirement was to use Java 8. So as long as the project worked with Java 8, they actually didn't care about what Scala version I was actually using for compiling this. And in fact, I think that with the Scala 2.7, Java 8 was not going to work anyway. So I did have to do the upgrade.
Okay, yeah, thank you very much.
You said you removed the tests, but it seems to me like the tests would be very useful for figuring out if the old code actually worked.
Yes, I removed the test because I was getting annoyed by a huge amount of compile errors. And given that there was no actual change in the code and that the customer had their own way to QA this, and he was happy with it, and he didn't want to pay more, so basically that's where I left. Ideally, I should have fixed the test. I should have upgraded to a more recent Scala version, like 2.12, 2.13. But you know, like, customer had limited funds and they didn't want to keep pouring money into this. They just wanted to solve a very specific problem.
Imagine that in 15 years from now, you have to do the same thing for some Scala code that is written today. Do you have hopes that things are better now, or it will be the same thing?
It's definitely better. I mean, the bad thing is that Bean Tray is gone and many other artifactors are gone. Because, for example, when the Play framework migrated everything from Bean Tray and published everything into Maven Central so that people can use all Play framework versions right now. But that was a huge effort. But that's only done by Play framework. I am not aware that many other frameworks or libraries have done that. So the ecosystem in Scala is way, way better. The only thing is that the history is gone for many things because of these artifactors. But I mean, compatibility between Scala 3.3 and 3.4 is way better than what it was from 2.7.3 and 2.7.4, for example. So yes, we are way better from my point of view.
I was just wondering, how confident are you that Maven Central will stick around, and what do we do if it goes?
Can you repeat the question? I didn't understand.
I was just wondering, like, it seems like the one Maven repository that's still working is Maven Central. And do you feel confident that it will still be here in 10 years' time, 15 years' time? And what do we do if it goes?
If we go away, we are going to have bigger problems because the whole Java ecosystem depends on that. And I mean, the Java ecosystem is something that there are many huge companies depending on. So, I mean, we already saw a while ago that the guy maintaining Maven Central was complaining because like 90% of the request traffic was coming from 1% of the IP address space, and he had to start rate limiting because there was a lot of money that was being charged because of that. And these companies could have actually invest or donate or whatever, but they are not doing that. So at least for now it's public, and that's good. I hope we don't need to worry about that because there is going to be a lot of work for everybody involved in the community if that happens, but I hope it does not. In the case of big companies, typically they also have like their own Artifactory server internally where they are caching all the dependencies that they have so that in case that this happens, they are not going to be affected. Maybe we could have something similar with mirrors in order to mirror whatever Maven Central has, and I think that can be pretty helpful, where it's a non-negligible amount of work and money in order to do something like that, but it will be pretty nice.
I have a few questions actually. What was the size of the code base and how long did it take you to compile it?
Well, the size of the code base, it was something like 5,000 lines of code, if I remember correctly. So it wasn't huge. It wasn't tiny, but it wasn't huge. And the other question, can you please repeat it?
How long did it take to you to work to get it compiled?
It was work of a few days, less than a week, but I was not like fully focused into that. Like I was picking it up, spend a few hours, get frustrated, then wait for a few days, take this again with a fresh mind, ask on the forums, then take another break and get back in a few days, and that was it. I mean, the total amount of work was less than a week, but over a few weeks, maybe 3 weeks or something, I don't remember.
Okay, thank you. Any other questions? Thank you very much.
Thank you.
Can you hear me? Yeah. Okay, hello everyone. I hope you're having a great Scala IO thus far. You might be a bit sick of hearing of monads and functors by now, so that's good, because we're going to throw functional programming under the bus. Don't worry, it will have object-oriented programming to keep him company. So who am I? My name is Gaël Renou. I'm a staff engineer at Datadome. I've been a developer for about 20 years, a bit more. Coding in Scala for more than 10 years now. I also have a few open source projects. Some of you may know about Transactio, which is a ZIO wrapper around Doobie and Anorm. So yes, I can do functional programming actually. But more relevant for this talk is going to be Gaston, so more on that in a minute. So what's Datadome, just quickly? We're a bot and fraud detection system. So we tell our customers if whatever's connecting to their website is actually a human, a customer, or if it's a bot coming to scrap their content or try to buy all of the Taylor Swift tickets to the concerts to sell them for twice their price on eBay. And so it's kind of different from what I suspect most of you do, actually. So why am I here talking about a low-level performance in Scala? For actually most of my career, and I assume that's true for most of you as well, I've been working on mostly web applications. Or so you know, HTTP request, very likely a database in the background, maybe a message bus, something like that. And so this kind of systems relies heavily on IOs, and that's usually the bottleneck, right? The bottleneck for this is the input-outputs of your systems. Now what we do at Datadome, and especially on the part that interests me, which is the streaming engine, the behavioral detection, it's, okay, we have some I/O, right? 200,000 requests per second, that's quite a bit of IOs, but because it's distributed over about 100 nodes, it's not that much IO to the point which IO is not our bottleneck anymore. We have around, again, just for the behavioral detection, 300,000 rules to apply to each and every one of those requests. That takes a lot of CPU. So to the point now, our bottleneck is CPU. It's no longer IO. The other project I am going to use as an example here is Gaston. So Gaston is an open source project of mine that makes schedules that actually I created it for RPG conventions. People come and say, hey, here are the games I'm proposing for the convention. People say, hey, these games look great, I want to play that. And another one say, hey, I want to play that one. And Gaston's job is to provide you schedules that's going to satisfy about everyone. Never satisfies everyone. It's open-ended, like you never have exhausted all the possibilities, so you just let it run until you have a satisfying solution. And it has pretty much no I/O, because at the beginning you load the initial situation, you start working with it, and you have no more I/Os apart from sometime outputting whatever is the best schedule you find until then. So very little I/O, pretty much all CPU, and because most RPG conventions do not have dedicated hardware, it typically runs on the computer of whoever is doing the schedule. So we're going to forget about the situation on the left right now, which is the one most of you know, and we're going to focus on the two on the right, where CPU and, to a lesser extent, memory are our big bottlenecks. Okay, so quickly, the agenda for today. So a bit of a general principle of how I go optimizing the process I follow. Then we'll go into the code. A bit on just basic iterations. We'll look into collections, then your own classes, how you can change your structure. And then we'll look a bit at what it looks to when you go all in for performance, right? We are going to sacrifice everything to make our data structure as performant as we can. Okay, general principles first. Honestly, optimizing for CPU and memory is just basic three-step cycle: monitoring, benchmarking, implementing, and then back to monitoring, and that part is important. So step by step. Monitoring, the first part is obviously finding your bottleneck. There's no point trying to optimize something that's 1% of your application time. Tools I use typically are just, honestly, basic tools. JDK Flight Recorder, so it's included in your JDK distribution. It lets you just record whatever's happening in the application. Because it has pretty much no overhead, I strongly recommend you use that in production. That's where you're going to get the best value. Once you've done that, you open your recording in Java Mission Control. This one you have to download separately, and start examining whatever's happening in your software. The main tool I use in GMC, so just checking who's familiar with flame graphs. About half people, 2/3. Okay, a flame graph is just basically it's showing you how much time you spent in each step of your stack trace. It tells you, hey, at this level of the stack, well, that's where I spent all my time. And when I go up, it tells me that's the next call in the stack trace that's taking all the time. Here, for example, where the cursor was, you can see that I'm spending quite a bit of time in actually sorting, so maybe optimizing that part is interesting. However, optimizing the very, very narrow flame at the end is useless, because even if it makes that go 100 times faster, it's not going to make me win much on the application. So that's a really great tool to figure out where optimization can bring you something. Okay, so you've monitored, you figured out, hey, that's something I want to improve, I have a few ideas, let's try it out. Okay, first rule of benchmarking is use a benchmarking framework. Okay, we've all started by just doing system.current time in millis and doing a subtraction and looking at how much time it took. That's a terrible idea for actual benchmarking. Use a benchmarking framework. I use SBT-GMH. It's simple, it works as an SBT plugin. Another thing you should do, especially if you're starting to use macros and stuff like that, is take a look at the bytecode using a Java app. Because that's going to tell you, well, if you want to check your macro is actually producing the same code as what you expected, you can easily compare. So yeah, nobody likes to read bytecode. It's not pleasant at all, but you sometimes need to. It won't help at all with the optimization that are done in the runtime. Use directly production data, so you need to anonymize it first if you have confidential stuff, for example. But try to be as close as possible to code, to production data. And honestly, often the hardest one is to be close to production infrastructure, because it's going to depend on where you work, on your company, obviously. But not all companies have the money to have the benchmarking environment that's exactly the same as your production environment. Like, it can be prohibitively expensive. But again, try to choose the proper, as close as possible. I'll have a few examples later of benchmarks that gives different results depending on which machine runs them. And finally, especially if you're using non-dedicated hardware, like running on your local computer, run the benchmarks multiple times. Because sometimes you're just going to see a difference, and when you run it another time, it's completely disappeared, because the difference just happened to be that something was running in the background at the same time you're doing your benchmark. So run them multiple times and check their coherence. They're consistent, I mean. And, well, once you've benchmarked everything, it's time to implement, only if you think you're winning something that's worth it. Because destroying everything behind you is not a good idea. You're going to have to maintain that code, and sometimes just optimizing early for something not big, it will prevent you from doing a bigger optimization later, because your code will have become so unreadable, you won't be able to figure out something. So make sure what you're doing is worth it, and then you're back to monitoring, because as I said, sometimes the benchmark is not representative of what happens in actual production. So once it's implemented, once it's back in production, you monitor again to make sure that, hey, it worked. A bit of on theory. I'm not saying theory is unimportant. It is important when you want to optimize, because that's where you're going to have your ideas about what you can improve. However, modern systems are fucking complicated. Between compiler optimization, JIT optimizations, everything that gets optimized at the runtime, but also everything that gets optimized at the CPU level, makes for extremely complicated systems. You can have an idea of how they work, but honestly, at the end of the day, the only way you can get a proper picture is by experimenting. You have to benchmark, you have to monitor, you have to try it out. One point I like to bring a bit about this is what I call the big lie of the big O notation. Like, you learn at school, like, hey, logarithmic is better than linear, which is better than hyperlinear, which is better than quadratic, etc. That's wrong. That's not the case. Logarithmic algorithm is not better than a linear algorithm. The problem is the big O notation, by definition, completely ignores constant factors, which means that it will help you figure out how your algorithm is going to evolve as you put more and more data into it. It's good for that. However, it's not going to tell you this algorithm is better than that algorithm. One of the biggest examples I like for this one is heap sort versus quick sort. Heap sort is hyperlinear in the worst case. Quick sort is quadratic. So quick sort on paper is worse, right? Except that for the past few decades, every single sorting function in every language has been implementing using quick sort. Recently, well, over the past few years, we've added more and more heuristics to make sure we're not in the worst case. But quick sort is just flat out better than heap sort for pretty much every conceivable use case, because the way it's implemented makes a much better use of its time. So yeah, beware of the big O notation. It's not going to tell you that algorithm is better than this one when you're comparing two very different algorithms. Before I jump into the very technical stuff, so my benchmarks have been done with Scala 3.5, SBT GMH, latest version, the Tamarin GDK, version 21. All my benchmarks show durations, so lower is always better. And finally, you have the URL of the complete benchmark at the bottom if you want to get it. I'll put it again at the very end with a QR code, so don't worry if you didn't get it now. Okay. We're going to start very simple with just really basic iteration. I have the simplest function imaginable. It does literally nothing. It returns its first argument. And we're just going to run a for loop and a while loop. And I want you to just think for a few seconds, what do you think the benchmark will look like? So if you know Scala, which I guess most of you do, you know that a for loop is actually chaining flat maps and filters. So yeah, you'll expect the for loop to be a bit worse. It's not a bit worse. It's, yeah, there's not just a comparison. The for loop is terrible. However, this is a very unfair comparison, right? Because my function does nothing, literally nothing. The runtime is going to optimize it out of existence. So I'm really comparing the loop time. So okay, while it's almost instantaneous, for takes some time. Okay, what happens when I do something? I've added a simple addition. Okay, still not a very complicated method. Okay, a bit more fair. And that's just an addition, right? If you start doing something like a multiplication or something really complicated, like a division, the gap between the two gets smaller and smaller. But still, simple additions is sometimes not much less than what you're doing, right? So I have done loops where I've been doing things that were just a bunch of additions chained together. In those cases, yeah, there's a difference between a for loop and a while loop. And by the way, if you're stuck with old version of the JVM or of Scala, it's way worse before, especially, actually, it's not even Scala, the main culprit, actually. The JVM got way better at optimizing. If you're on JVM 17 or even 11, it's way worse than this. However, Scala 3 came with something very useful, which is inline def macros, which very simple, because yeah, while loops are ugly, right? Nobody likes to write a while loop. So you can just write your very own C-style for loop in a macro, and you're going to get just exactly the same benchmark. And by the way, this is one of the cases where looking at the bytecode is useful, because if you look at the bytecode, you'll see that both using fast loop or a while loop has exactly, literally the same bytecode, to the point. But, okay, that's, that's just basic iteration, right? We don't do that often. We usually work with collections. So collections is one of the data types we're going to use the most of all the basic data types, and it's probably the one that's going to impact your performance most. So let's start by iterating a collection. Will be a bit more complicated. This time we're going to do a function that calculates the square of the length of a string, and we have a collection of string. We just want to iterate on that. Multiple ways to do that through functions. So you can just do a map and then sum. You can be smart and do a view before the map. You can do a fold left, for loop, while loop, recursion. And we're going to check this out on arrays, vectors, and lists. Again, just think for a bit. What do you think this would look like. Well, it's going to depend a lot on the size of the collection. So because this is simple iteration, actually the longer the collection is, the more time the runtime has to optimize. The first interesting thing to note is that arrays are faster, actually. If all you care is CPU performance, yeah, an array is faster. And please note that this is an array of strings, which is actually not the best use case for arrays. If your array contains, your collection contains basic types, ints, doubles, whatever, arrays are lightning fast. No heap, all on the stack, and the CPUs are really, really, really good at optimizing calculations on arrays of small primitive values. Another interesting thing to note is that the view does not actually help on arrays, and it doesn't even help that much. But obviously, this is not a great use case for view because there's only one function application before the reduction at the end. Other than that, well, fold left on small iterations is not great. Not great. The for and while loops are doing better. On bigger, when the collections, when the JVM has the time to optimize, it gets pretty much the best one, right? Main takeaway, yeah, arrays are fast. The smaller the collection, the better, but arrays are fast. Something else we often like to do with our collections is just, aggregate things as we go. So not much. I thought I'd throw this one in because, again, this was something that was actually pretty different in Scala 2. Because in Scala 2, prepending was actually significantly faster on list buffer than on list, for some reason. On Scala 3, as you would expect, appending to a list is pretty fast. Prepending, sorry, to a list is pretty fast. What I mean by appending to a list is obviously I prepend and at the end I reverse. I'm not prepending every single element because that would be terrible. There's no need for a benchmark for that one. I also compared with Java's linked list just to have a basis. And yeah, Java's linked list, it's doing okay, but not great. Okay, nothing surprising here. Scala's better than Java. Yay. Okay, we're going to talk about sets. And we're going to talk about kind of the emblematic operation on sets, which is contains. For very small sets, arrays are good, actually. Just a simple basic array. And so here I'm trying about 1,000 lookups, 50% misses, 50% hits. An array is pretty good, actually. It's better than both Java's and Scala's hash set. Obviously, on very big collections, very big sets, it's going to be worse, right? But that's not the only one. Scala's hash set is slow. Scala's hash set is disappointingly slow compared to Java's hash set. I'm not entirely sure why, to be honest. There may be a number of reasons. It may be better optimized for other operations, like appending. Because remember that this is a Scala immutable set, while Java is mutable. Not entirely sure, but it's consistent across all machines. Scala's hash set are slow. However, we do have options if you want to optimize this. Sure, you can, go back to Java's hash set if you really need that. But there are a few alternatives, actually. There's something in Scala called a bit set. So a bit set, the basic idea is you're just going to have a set of ints. And to represent a set of ints, you can just use a bunch of numbers. With a single long, for example, you can represent a few ints by saying, hey, if int, n is present, well, the nth bit of my number is going to be flipped to 1, otherwise it's 0. And then my long is able to represent a short set of ints. Put a few longs together, and you're able to represent a great number of ints with extreme economy of memory and very good CPU performance. So, of course, this comes with two slight disadvantages. The first one is that your objects need to have an ID. Honestly, that's not that big of a deal, because a lot of the times already will, and if they don't, it's not that hard to have a pretreatment where you add an ID to everything. So, having the object have an ID is not hard. The problem is that, well, your set doesn't contain the values anymore, right? It's nothing more than a filter now. If all you need is a filter, that's fine. If you also need to pass around the actual values, you're going to need something else. Maybe an array. Obviously, if your set is a set of ints, just use a bit set directly, right? Don't even ask. We can, however, do even better. Okay, array set is just a fancy wrapper as an opaque type around an array of booleans. And I'm just going to say, hey, my integer n is in the set if at the position n in my array I have boolean. That's lightning fast. Even better than the bit set, although with very large sets, it starts to catch back a little bit. Obviously, here there's another big issue, which is memory consumption is horrible compared to a bit set, especially if you have a sparse set, like millions of possible values, but only 4 elements, you're wasting a ton of memory. That might actually be worth it. And that's something I cannot answer for you because that's going to completely depend on your actual use case. Maybe you really are ready to exchange like a few kilo or megabytes of memory to gain a bit of CPU. Okay, so yeah, just short recap. So bit sets, array sets, there are solutions, there are trade-offs. You need to have an ID, which is easy. You cannot get the value back, which means you might need another collection. And in the case of array set, the memory cost is terrible. What about maps? As you can expect, Java's hash map compared to Scala's hash map has pretty much the same issue because, well, hash maps and hash sets are pretty much the same structure actually underneath. So yeah, same issue. Scala's hash map are slow. Scala's hash maps are very slow. Again, you can have a solution as an array. Instead of having, if your keys have an ID, okay, forget about the keys. You're just going to store into your array the value at the ID of the key. Unlike a set, here the issue is more that, well, there's no real way to represent something missing from your array, right? Except if your type B is an option, okay, easy. But otherwise, you're going to need a default value. One big advantage of this, however, is that, again, if your values are primitive, like ints or doubles, this is going to be extremely effective because you're going to have an array of ints or doubles, again, all on the stack, super fast. And if you have missing values, well, you might want to resort to the old solution of, hey, I'm going to put -1 to denote a missing value. Yeah, it hurts as well, I know. But if you have an array of double, don't put an option, right? It's going to break all advantage you have just gotten by putting an array instead of anything else. Again, super efficient with a few disadvantages. And again, just as said, well, the keys are not in the map anymore. So if at some point you want the keys themselves, you're going to have to find another way to pass them around. Okay, so that was about our about collections. Let's go a bit into our own class structures, and we're going to explore what's probably one of the first things you learn when you do try to optimize a bit. Well, one of the first things that you're told, I've heard a lot, is your class should be final. Because of course, if it's final, you know there's no polymorphism possible because it cannot be extended. So the compiler or the virtual machine is going to be able to optimize it a lot. Another pretty big difference is, am I going to do it as a mutable class or not? Yeah, I know, mutable case class, very ugly. So this is a basic statistics class. It's not that different from something we actually use at Datadome, also obviously very simplified. We're going to keep up a bunch of statistics for strings, and we're just going to iterate over a collection of strings. And for every string, we're going to increment our statistics and get the results at the end. Okay, so I'll leave you just again, a second. What do you imagine this would look like? Again, it's going to depend a lot on the number of iterations. This is completely going to depend on how hot the JVM is allowed to get on your iteration. On a small, first one thing to note though is that final versus non-final makes pretty much zero difference. And thinking of it, that's not that surprising because, well, that there is no subclass and that it can be optimized is something the runtime can figure out on its own. It doesn't need you to tell him, hey, this is final, there's no subclass. Yeah, it knows that. It has access to everything. So final, non-final, that, by the way, that does not mean do not put final. Final is still very useful just for type safety on your case class. But it's not going to have any effect on performance. However, for a small number of iterations, mutability, well, unsurprisingly, is doing significantly better because you're not recreating a new object every time. What's interesting is that for a lot of iterations, the difference pretty much disappears. It's very, very slight gap, a little bit better for mutability. The thing is, this is a very simple loop, and that's something both the JVM and then the processor are very good at optimizing. Because, well, even a human being can see that if all I'm doing is just, okay, copying the case class and, updating the stats, well, I could just reuse the previous object because the previous object is going to be thrown out, so whatever. That's something the runtime is good at optimizing. So it's going to optimize it. And in the end, I was honestly kind of surprised that it took it that long to figure out that it can be optimized. So, but that's not exactly fair, right? That's not exactly fair as a test for two reasons. One, because as I said, it's very easily optimizable from the immutable point of view. But it's also unfair to the immutable version because you're not taking any advantage of the fact that it's immutable. You're not keeping all the version of your stats. You're throwing it away every time. So let's try something different. Let's play a little game. Our game state is just going to be represented as our position in space, XYZ. We're going to be able to move around in all 6 directions. And we have a goal that's going to be evaluated giving on our current position, telling us, hey, how good are we right now? The immutable state is just going to, as usual, have an updated method returning a new move. And then the mutable state will have 2 methods, one to update the current state with a move, and one to reverse, actually, the change we just did. And what we're going to try to find out is, okay, I want to find the best possible combination of 4 moves to improve my goal. So obviously, it's a pretty naive algorithm on both sides. As a human beings, we immediately see, hey, wait a second. If only the end position is what matters, a lot of moves combinations are the same, right? You could optimize this like, yeah, doing east, then west, then east, then west. Yeah, that's the same as right now. So there's no need to evaluate all of this. In both cases, I do the same, and it will do for that. Now, on the immutable part, it's pretty easy, right? I iterate over all possible moves. I have a new position. Then I iterate over all possible second moves. I have another position, etc. I do that 4 times. And at the end, I look at my end position. Is it better than whatever best position I've found until then? And if I found, I change it if necessary. All good, easy. The mutable versions is a bit uglier because every time you've done a move, you've actually changed your state. So before you try another move, you have to revert what you just did. So you're constantly updating, reverting, updating, reverting, updating, reverting, etc. for the number of possible moves at the power of 4. And at the very end, because you've reverted everything, if you want to be able to output the actual target position, you have to reapply everything again. So obviously, it's not hard to figure out which code looks better. But regarding performance now, mutable's better because, yeah, sure, you need to revert stuff, but even with the reverts, that's just a few variable assignments, right? And just a few additional variable assignments are nothing compared to creating new objects. What's more interesting is that going from 100 starting position to 1 million starting positions we're going to evaluate changes pretty much nothing to the ratio between the two. It's just doing a times 10,000 on both sides. Here, the JVMs appear incapable of actually optimizing the immutable out of it. In this case, mutable wins. Even though, again, that was a case where, well, there's some interest, right, in keeping an immutable object because you're going to go back to that immutable object. Does that mean you should always go for mutable? Of course not. For example, if you want to keep a history of every single possible position in the past, then yeah, if you're going to need those objects anyway, you might as well go with immutable and keep the old ones. But that's not that often the case, and most of the time, going with mutable is going to bring you some gain in performance. And yeah, I know it hurts. It breaks. Potentially, you're breaking a lot of type safety stuff. But again, is it a trade-off you're willing to make? And I cannot answer that question for you. Okay, all this was, until now, pretty, not basic, but just punctual improvements, just a slight changing here, changing there. What if we go really all in? We're going to rewrite our whole domain. So this is a very simplified version of what's happened inside Gaston to optimize the schedule. So I'm going to, I have a bunch of persons defined by just their ID and name. Topics have an ID and name. They also have a set of mandatory persons for RPG conventions, as that's the game master, of course. It needs to be on the game. A minimum and maximum number of persons. And your problems, the thing you're trying to optimize, is going to just be a set of topics, set of persons, and a bunch of preferences expressed by everyone. And in the end, you're going to get a schedule, which is, okay, here are my topics and the associated persons. Preferences, just a simple hierarchy. Preference is going to be a person, a topic. For example, for people to say, I want to play this, it's going to be a person, a topic, and a score. We also have the case of, yeah, two persons are good friends, they really want to play together. Two others just cannot stand each other, there's no way they're playing together. All of those constitute preference, and to score a preference is pretty easy. You look into the record, you look if it's satisfied, and if it is, well, you have your score. You add all of that for all the records, you have your final score. Easy to read, easy to understand. Okay, how do we optimize now a schedule? So that's a pretty big chunk of code, but it's not very complicated. I'm going to go through all possible pairs of topics. So I start with an existing schedule. I'm going to go through every possible pair of topics. In each of them, I'm looking to all optional persons. Optional, of course, I don't want to remove someone who's mandatory. And I try, okay, if I swap them, is it better? And if it is, yay, I found an improved schedule. So that's just for swapping persons. Then I need another piece of code to check out what happens when you move persons without swapping them from one topic to another. That's a bit more convoluted because I need to check for that minimum and maximum values are still respected, but nothing too complicated either. In both cases, I stop as soon as I found a schedule that's better than the one I already had. Okay, pretty basic, pretty simple. Now, starting with a naive approach, as okay, well, I'm going to implement everything I've preached, right? Every single set that's just looking for content, I'm going to replace with array sets. Every single maps, I'm going to replace with array maps. A good thing, everything already has an ID. I'm going to use arrays as collection as much as I can. And I'm going to use macros, inline defs and such for doing loops and folds and stuff like that. Try to optimize as much as I can. And I get an improved version, which is so significantly faster on this machine. Doing the exact same benchmark on another machine that was less powerful led to actually pretty much no improvement. Very same benchmark, and the results were consistent. Multiple run of the benchmark, different machines. In one case, the significant improvement, the other, nothing. So again, yeah, try to be as close as possible to the production if you can. However, we can do better. Because, okay, who the hell cares about maintainability? Who the hell cares about having readable code that you can modify? None of those fancy schmancy object stuff, okay? Arrays everywhere. We might have somewhere the names of the person and topics so that we can output something readable. But for actually improving, we're going to work on only arrays. So I won't have an array of topics. I will have an array of, well, all the topic IDs, another array for all the topics minimum value, then another array for all the topics maximum value, same for the persons. And now the preferences, instead of being a set of clean hierarchy, letting me clearly see what kind of preferences exist, it's a bunch of matrices. And okay, so my person to topic preference is okay, first look at the person ID, then the topic ID, I have the reward. Which means it's actually pretty hard to evolve this, because as soon, imagine you want to add a new preference. Like, so you want to add a preference because some people say, I don't want to be in big groups. I want to have a preference for small groups. With the older one, it's easy to implement, right? Just a new subclass with a new rule. Here, you have to figure out how you can implement that as an array. And then you have to actually modify the scoring method, because it's not self-contained anymore, right? We've completely forgotten about object orientation or anything. Everything's in the score method. You might also notice the extremely ugly fact that because the schedule is mutable now, I have both the current score and the score that's been cached when I've created the schedule. Which is interesting because in practice, when you run the improvement, typically the first few attempts are easy to improve, but after a while you got a lot more attempts where it doesn't improve the schedule than attempts where it does improve the schedule. So I'd rather, because I'm going to keep an existing schedule for a while, I'd rather cache the score. And my algorithm also gets a lot more ugly, right? The beginning is pretty much the same, but then when I've swapped the persons, so I need to check if my current score is bigger than the score I have cached. If it is, then great, I can do a full copy, because the score is not the only thing I've cached. A simplified version, you can look at the actual code for all the other stuff. And otherwise, if my schedule was not an improvement, well, just as before, we had in the game, we're going to have to unswap everything. The opportunities to fail something here are huge, right? Because you have array indexes everywhere, it's, by experience, really easy to mix it up and look first the topic ID and then the person ID instead of doing the opposite. And you cannot have opaque types here because they're just going to be used as index in arrays. So the compiler has to know those are ints. Really easy to mix it up, really easy, harder to make changes. That's not a great combination, right? However, and this was constant on all computers I tested it on. The all-in version is way faster, like 3 to 4 times faster. Because the scoring is way faster, looking into this matrix is way faster to find the score of someone than go through list and then go through list of preferences. We have a lot of arrays of primitive values, which again can be very easily optimized by the compiler. If you don't know about, so obviously the CPU cache, which is good, but also the compilers nowadays are super good at doing multiple operations at the same time on a vector on an array of primitive values. If you don't know about vectorization, you can take a look. But the basic idea is that a lot of CPU now implements the idea that you can do multiple operations at the same time in a single CPU command. The code's horrible, and honestly, I'm forcing a bit the trait because, yeah, it's not great, but it's still readable. That's a heavily simplified version. Now imagine that on an actual production system, which is going to be much more complex than that. The code is going to become hard to read fast. And sure, you can do stuff to make it easier. You can wrap it in a bunch of pseudo classes, which will only contain methods. You're trying to do macros. You're going to kill your compile time to make it a tiny bit more readable. But it's nowhere as readable as the initial representation. But then again, it's 4 times faster. Okay, where does this leave us? Main takeaways: arrays are fast, mutability is fast. That shouldn't be much of a surprise anymore. it's actually surprising. Mutability is fast for longer than you think it would be. Even if you had to do reverts and stuff like that and complicated stuff when you go back and forth between your modifications and canceling them, it's still better than copying a lot of the time. Arrays are fast, and I mean not only when you iterate through them, even as sets, for very short sets. Like, honestly, when I check the tipping points, depending on your computer, depending on your version and stuff, it's somewhere between 10 to 20 elements. Over 20 elements, you're almost always better with a hash set. Below 10, it's likely that just an array is going to be better. Don't be afraid to use macros when necessary. And that's something that's easy to check out actually in the bytecode. So easy optimization to check. And again, you're sacrificing some compile time. Okay. Obviously, do not do that on your whole application. That's why the monitoring part at the beginning is so important. You need to figure out what your hotspot is. You optimize your hotspot, but please do not transform your entire application to become a bunch of arrays of ints and doubles and matrices, because that's going to be horrible for you in the future. Also, again, I'm repeating myself, but please benchmark and monitor with production code and data, because that is going to influence a lot. The JVM has something called speculative optimizations, where it's actually making guesses about, hey, actually, given the data, that part of the code is never executed. Okay, so I can completely optimize it out. Except sometimes, after a while, it realizes, okay, I was wrong. I need to put it back. This is the kind of things you'll only see if you're using production data. A few reads quickly, if you want to learn more about a bit about the theory behind all of this. The first one's a very short article, short and easily read article about how does the JIT compilation works. All of the links are also in the README of the benchmark page, repository. Sorry. The first one is going just to, it's not very long, it doesn't go to any depth, but it's going to give you a lot of keywords about what's happening in the JIT compiler. And then you can search for those specific keywords to get more information, to get, okay, what exactly does that mean? The second one is kind of the opposite. It goes extremely in depth about what happened in modern CPUs. Unless you're a CPU programmer or a driver programmer, most of it, I did not understand most of it, honestly. Maybe some of you are better than me in CPU programming. That's entirely possible. That's not all my area of expertise. But just skimming it is going to give you a good idea about where modern CPUs are right now. But what kind of optimization you can expect and what kind of stuff is going to improve your situation. And the last one is a short article that was done about the very first thing I showed, you know, how to implement a C-style for loop in Scala, pretty much comes from there. And it goes a bit more in depth about, okay, what's so bad about Scala's for loop and the way it ends up in the bytecode. So again, you can take a look. It's actually potentially worse than what you think when you have something like imbricated for loops, non-local returns, etc. Those things are horrible when they turn out in the actual bytecode. There's a lot of things I could have talked about as well, but I'm kind of limited by time. I did not talk about multi-threading. I did not talk about a bunch of libraries that can help you. You're going to have to find that on your own, or I'm, of course, available for any questions. The QR code at the top is corresponding to the repository.
Thank you. Very, 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 very interesting. You didn't mention I saw an article on causal profiling.
On, sorry?
Causal profiling. It's a technique where you can add some gap between calls randomly, and then study after where the gap are significant during the test, so find the parts that should be optimized.
Okay, I did not know the term, so I'll have to take a look, honestly.
You look for causal
profiling,
and I will be very interested to know if it's something that should be used, maybe used, I don't know.
Honestly, I cannot answer because I do not know. I'll have to check it out. But thanks for the suggestion.
Any other question? Thank you.
It's good.
Puisque tu es là, merci, on récupère
So my name is Howie. This presentation is about better Scala builds. So about myself, I've been an open source developer since 2012. Lots of open source Scala projects, projects like Ammonite, Mill, OSLib, Pickle, FastParse, and many others. I also work professionally at Databricks and Dropbox, working on developer tools. So things like CI systems, integration testing systems, multi-cloud infrastructure, IDs, build systems, and so on. I'm the author of the book Hands-on Scala Programming. So the agenda for today is we'll talk a bit about what is Mill. We'll go into a bit more detail into why you may want to use the Mill build tool versus what you already have. And lastly, we'll spend some time talking about how does Mill work. So the first point is maybe what is Mill? So before I go into this, like who here has used Mill before? So some of you have, most of you probably haven't. So Mill is an open source JVM build tool. The project's not that new, it started in 2017 and originally targeted Scala, but now also targets Java, Kotlin, and other platforms. So it does the same thing as SBT, Maven, or Gradle, more or less, but aims to be better and easier to use than SBT, Maven, or Gradle. In terms of Maven, Gradle, it's a lot faster. In terms of SBT, generally it's a lot easier to use and fewer things to go wrong. The documentation is at millbuild.org, so those of you who have your laptops open or your phones open, you can go there and check out more details there that I can't go through in this talk. So to begin with, a simple mill build looks something like this. So on the left, you have the build.mill file. This is equivalent to build.sbt or build.gradle or form.xml, and it defines the structure of your project. So we have the package import boilerplate, we have an object that extends module, we have Scala version, some dependencies, the standard kind of triple format, similar to what Gradle uses, and you have a nested object, which is the test module, and it pulls in the dependency on the utest library and configures the appropriate test framework. So far, nothing here should be too surprising, and I can show it to you here live. So if I pull this open, cd -- simple Scala, and I can pull up the relevant. So let me put this down a second. Okay, so on the left, you see the same build we saw earlier on the slide. On the right, let me make this bigger, I have my terminal. I can run mill compile. The first time it's a bit slow because it needs to boot up, but after that it gets fast, just like any other JVM application. Foo.compile. I can do foo.run. In this case, the application requires some command line parameters. Application requires a -- text flag, so I need to pass in -- text. Let's say hello world. And this is kind of a dummy application, just uses the Scala tags HTML library to render some HTML to stand it out. In this case, we say h1, hello world, close tag h1. If I go back to the build file here, we can do foo.test. You see this just runs a test suite, supports all the Scala test frameworks. Foo.assembly. This generates assembly, but if you want to see what the assembly is, you can use show. So this generates assembly, which is a kind of a fat jar file that you can run outside of mill. So I can run the assembly with -- text hello world, and it just prints it out. So far, nothing here is that surprising. Guys have seen this all before. These are standard kind of build tool functionality. And the main thing that's interesting so far is that your mill build is a Scala program. And it's not a Scala program in the way SVT is a Scala program, which is a kind of really complicated DSL built on top of Scala with lots of additional functionality. It's a Scala program in that you have objects. The objects can nest within each other, as objects do. Objects can have methods, as objects do. And the methods can call each other or be inherited or be overridden by other methods. So although this is Scala just SPT, hopefully it's a bit more familiar to you. And we'll see some more important ways in how that impacts mill later. So if we saw the demo, And that's what is mill. So the next obvious question is why mill? You're already using SBT, maybe some fraction are using Gradle or something else, or Basel. So why would you use the mill build tool? And for people coming from the Scala community, I think the main selling points for mill are these three. So it's harder to use incorrectly. Like there's not that many ways you can go wrong. It's somewhat more understandable than SBT, which is a common complaint. Like you have a build, your cargo collecting things off the internet, there's no way for you to figure out exactly what you're doing or know what you're doing. And lastly, it's much more extensible. So, SBT has a huge plugin ecosystem. Mill also has a plugin ecosystem. But Mill doesn't need plugins as much as SBT does because you can often just extend it yourself to do what you need to do rather than what some random plugin author on GitHub needed to do. We'll go through these in turn. So first, about being foolproof. So one of the things we did with Mill is we ran comparative benchmarks against the other popular JVM build tools. We have comparative benchmarks against SBT, against Maven, against Gradle. And for this presentation, I'm going to mostly talk about SBT, since that's what we use in Scala community. So I took the Gatling code base. Gatling's a popular kind of open source load testing framework. They now have a startup around it, I believe. And it's a kind of a medium-sized Scala application. So 80K lines of code, 800 files, 20 sub-projects. Not big, not large, kind of medium size. And I took the existing SBT build and I converted it to Mill just manually. It took about maybe an afternoon, not terribly difficult. So it's not a production-ready Mill build, but it's enough to get all the source files compiling and all the tests passing. So for purposes of comparison, it's complete enough. So the benchmarks I measured were the parallel clean compile all benchmark. You run SBT clean, you compile everything, including the test suite. Clean compiling a single module, incrementally compiling a single module, like let's say after you change a single file, or no compiling something. You just run compile after you've already compiled everything. What's the overhead look like? So SBT, as you know, has kind of two modes of operation. One is if you run SBT raw from the command line, SBT compile, SBT foo :run, or SBT foo/run, or foo/test. And in this case, the SBT spins up a new process each time and can be pretty slow. It also needs to initialize a large amount of in-memory state in order for this to work. And you can see that the cold SBT numbers are relatively slower than the hot SBT numbers in the middle. So hot SBT numbers are what you want to do using SBT, or you should do using SBT to make it faster, which is to create an SBT shell by running SBT in bash, running your commands in the shell. Whenever you update your SBT build definition, you need to make sure you run reload so you don't end up using out-of-date build definitions. If you run something takes too long, you control C, you need to remember to reopen your SBT shell before running your next command. And this is all a bunch of work, but in exchange for the work, you get much faster turnaround times because your JVM has a chance to stay around. Initialization can be cached. The compiler and bytecode can become JIT optimized, and generally it's much more performant, albeit some significantly more manual work. So Mill is very comparable to the hot SBT workflows in terms of performance. In fact, in some ways it's a bit faster. Like the parallel clean compile all Mills may be a third faster than compiling everything using SBT, even though it's the same files. So these are all just overhead that Mill kind of has less of than SBT does. But perhaps the main advantage here is that with Mill, you can't accidentally just fall back to the lazy but slow cold SBT, run things from the shell workflow. Because in Mill, you always run things from the shell, and Mill will just automatically do the right thing for you. Mill will automatically reload the build definition when it detects changes. Mill will automatically restart the server, keep it running. If it gets killed, but for some reason, if you control C, you kill the server, Mill will automatically restart the server next time. So although Mill doesn't really have much of a higher theoretical performance than SBT does if you use optimally, Mill is just much easier to use optimally so that you don't need to spend so much time thinking about your build tool. Another advantage of Mill is in terms of using plugins. So the Gatling project has the following plugins. This is a subset, there's actually more. And these are all actually things that are pretty straightforward that many projects, or almost all projects, will need to do. Most projects will need to create some kind of assembly jars to deploy the binary to run somewhere. Most projects want to run benchmarks. Jupyter is the most popular Java testing framework in the world, so many projects will want that. Scalafix, Kotlin, you want some kind of auto-formatter linter thing, which is what Spotless does. And in order to get this basic functionality, in SBT, in Gatling, in this case, we need to pull in 6 different plugins from 6 different organizations, from random people across the internet, and hope that they did a good job writing these plugins and making them correct and effective. So with Mill, Mill does still have plugins, and in this case, we still need a Scala Fix plugin. That's the external plugin that someone wrote for Mill. But by and large, most of the things that you do with Mill are built in. So for example, creating assembly jars, which is what most people use native packager for. Mill has assemblies built in, and I just showed it to you earlier. You just run .assembly, you get an assembly, you can run it. JMH, Jupyter, which is JUnit 5, Kotlin, the various linters like Palantir Java format or Scala format, all these are built into Mill. And again, like Mill doesn't let you do more than what SBT lets you do. It's really the same functionality in both sides. But Mill just lets you do it easier, so you don't need to go scrape the public GitHub repositories. You can find the right plugin for you to use and hope you don't choose one that's abandoned or choose one that's poorly maintained. You just use the one that comes with Mill, and it'll generally do a decent job, and it's good enough for you to get started and kind of go very far with your project. So that's about being foolproof, right? It's not about the power of the build tool, because SBT, as you all know, is extremely powerful. It's not about performance. SBT can be fast. It's not about flexibility. It's kind of just how easy it is to get the maximum out of your build tool. Get the maximum performance, get maximum functionality. Mill just gets you there much faster and easier than SBT does, even though it doesn't let you do that much more. So the next point I'm going to look at is the understandability. So SBT is kind of famously opaque and hard to reason about. People can copy stuff off the internet, people can copy paste their own build definitions. But if I want to ask anyone here, hey, can you please go write a static file preprocessor in order to preprocess our static files at build time so you can deploy them to S3, people might have trouble doing this effectively using SBT. Like they know Scala, they know JVM, they know Linux or whatever, they know web development, but to combine all this with SBT to write like a non-trivial pipeline, like not just setting flags, but actually doing logic, can be remarkably difficult. And after you do it, someone else coming in to figure out what your SBT build is doing can also be pretty difficult. And Mill really helps this by providing really good ID support and introspection tooling. So even if you're not familiar with Mill, your ID can help you poke around the build and really understand what's going on. And we'll see this now. So first is the Chrome profile. So I'm going to go back to my demo. And let me pick the Gatling. I think this should be the Gatling Mill code base. So this is a Gatling build for Mill. It looks about the same as Gatling build for SBT, but slightly different spelling of the various syntaxes. So that's not interesting yet. Let me put this down. So if I run Mill clean in my Gatling Mill code base, again, first time it takes a minute to start up your JVM, after that's fast. And I run _compile. So you can see it's doing a lot of things. There's a little terminal kind of prompt on the bottom right-hand side of the screen. You can kind of tell, it tells you what it's doing at any point in time, and it tells you how long it's been taking for each move. So for example, now it's running core, compile, seems to be stuck for a while, but now finishes, it makes a bunch more progress. A bunch of downstream tasks are available to run. And same thing happens with other tasks. So we've run the whole thing, compile the whole Gatling code base to about 23 seconds. Again, this is not much faster than SBT. In particular, it's hot mode. Gatling, Mill and SBT are similar in performance. But let's say I want to ask a question. Why did Mill or Gatling take 23 seconds to compile? Where's the time going? What's running in parallel? What's running sequentially? Where are my long polls that other people are waiting for? What can I do to make this faster if it is too slow for me? So in many build tools, it's pretty difficult to get answers to. You can kind of squint at the prompt that's scrolling by in the terminal and see what's being compiled and try and get some intuition. But Mill provides something much better, which is an automatic profile for every build command you run. So if I open up my my output folder, I don't know if you can see this, but there's this Mill Chrome profile file that's automatically generated. It's a JSON file in a particular format. And what it does is it is compatible with how do I get out of this? Okay, here it is. It's compatible with the Chrome's // tracing tool. Who here has used a Chrome tracing tool before? Nobody? So for those of you who don't know, Chrome comes with an automatic built-in profile visualizer for multi-threaded programs built into Chrome. It's used by default for people debugging web performance issues, but you can load any JSON file of the right format into Chrome. It's not a very complicated format. It just tells you when did something start, when did something end, what thread was it running on. And it gives you an automatically generated and interactive view of where your time is going. So I'm guessing most of you have Chrome on your laptops already. You may have used this UI before, but you can plug it in right now. It works. And just like that, I can see where is my time going in my Gatling mill build. So you can see at the start, it's doing a bunch of small tasks. Maybe it's checking dependencies and whatnot. And then when it starts compiling things, you can see it compiles here, Gatling JSON path compile, commons compile, quick lens compile. After these three finish, core compile kicks off here. You can see it's taking a while, which is what we also subjectively saw at the terminal. And only after common compile finishes on the right, do a bunch of downstream tasks kick off. And another long pole, so to speak, is Gatling core test compile, which only after that finishes can the other test modules begin compilation. So this is interesting, and it's not just interesting from an academic perspective. Like this gives us a lot of actionable insight into what we can do. For example, we know that the CPU utilization at the front is pretty good. I'm using all my 10 cores on my MacBook Pro. But in the middle, the CPU utilization and towards the end, it gets pretty poor as we are not, although we have 10 cores, we're spending most of the time waiting for these single large modules to compile. And that gives us some actionable opportunities, right? Like, can Gatling core be broken up into smaller modules that can compile in parallel? That might help. You see a bunch of test modules like HTTP tests, JMS tests, some other test modules, all waiting for Gatling core test compile. Do those modules really need to wait for the entire Gatling core test suite to compile to finish? Or do we really only depend on some utilities library or test helpers or test fixtures that we could extract into a separate module and depend on, which would allow all of these downstream test modules to start compiling much earlier. And although the wall clock time may not be different, it will properly saturate, improve the utilization of our CPU around this time and help the wall clock time finish earlier. So this all happens automatically for free for you using Mill. Every single command you run, you just generate a JSON file. You all have Chrome. You're curious how long it took, load it up. And you can see immediately how many milliseconds every single command took, which ones were in parallel, which ones were sequential, and from there decide what you want to do to help speed up your build. So that's the Chrome profile, one of Mill's very nice built-in utilities. The other one is the visualize command, which offers another view on the structure of your code base. So coming back here. So imagine you're a new programmer who just joined the code base, right? You open up your Gatling code base, you see a whole bunch of files, a whole bunch of modules, 800 files and 80K lines of code, and you're wondering how does this build work? Like what relates to what, who depends on what, what's the structure of the build? Like I see the top level folder layout, but how do these things actually depend on each other and contribute to making the production ready application or code or module or library? So with Mill, you have the built-in visualize flag. I'm just going to search for it in my history. And Mill visualize, which we have down here, basically lets you ask, given a set of tasks, in this case, double underscore means wildcard, so double underscore compile means anything.compile, so all the compile tasks. Given a set of tasks, show me the graph representation of them. Like how do they depend on each other? So any build tool like Mill or SBT has lots and lots of tasks. Like you have IV dependencies, you have a source code, you have all sorts of small things that you probably don't care about. And by putting in double underscore compile, it tells Mill focus on these compilation tasks and kind of simplify away the rest. So you see now it generates 5 files, a dot file, a JSON file, PNG, SVG, TXT, the bunch of graph formats, whatever you prefer. If I open up the SVG, you can see that this is the Mill, this is the Gatling Mill builds compilation dependency graph. So you can see that core compile is indeed a bottleneck. This is exactly what we saw earlier in our profile. You can see that once only when core compile finishes can the downstream tasks here begin kicking off. And core test compile, again, maybe is another bottleneck that only when this finishes can the downstream test compilation kick off. And this isn't kind of magic, but this is just surfacing the data we already have in your build system and your project. So your build system already needs to know this stuff. Your build system needs to know who depends on who needs to run first, who can run parallel, who can run sequentially. ML makes it very easy for you to just ask the build tool, hey, tell me what's going on here. And here you can see exactly what the structure of my program is. And if I'm contributing to this code base, then this really helps me understand at a high level how this program is, how this code base is designed, not just as like a flat set of folders on disk. So that is, coming back to the slides, that is our visualize command. The next thing I'm going to look at is my IDE support. So MIL and SBT both have IDE support. They are both in Scala. IntelliJ VS could all support Scala. But we'll see how it's actually quite different between the two. So let me pull out again my Gatling. Sorry, put down the microphone. And I'll make this a bit bigger. So let me open up my build SBT. So pull up the right part of the code base. Okay, so like I said earlier, MIL and SBT are both Scala. They have very different syntax, but it's really the same kind of semantics or the same intent being expressed. So if we look at Gatling charts in MIL, I look at Gatling charts in SBT, like it's spelled differently, but it's really the same things happening, right? So Gatling charts, there's a dependency on Gatling core, there's a test dependency on Gatling core test. In SBT, the syntax depends on core, percentage, compile, test. Syntax is a bit different, but whatever, it means the same thing and we can guess what it means. Both have a dependency on charts dependencies, both charts dependencies have dependencies on T-digest and test steps and so on. So far you can see that both MIL and SBT have quite similar ID support. Maybe MIL has a few kind of spurious squigglies here that we are fixing the latest version of IntelliJ. What's more interesting is what happens when you start asking questions. For example, let's say I'm a new developer, I didn't know what library dependencies was. So you all probably know what library dependencies is, but there's also this kind of, imagine there are many other tasks you don't know what they do, right? So let's say you find tasks you don't know what it does. You know, IntelliJ can tell you library dependencies is a setting key of a sequence of modules, but it doesn't tell you much else. Like where's the docs, where's the meaning of this? It's just the type. So we love types, but types are not enough. There's more to code than just types. So if I jump to this, I'm left in a bunch of generated code that again tells me nothing except the type. So this is probably just a bug in SBT. Like sometimes it works, sometimes it doesn't. I know it's worked before, but let's say I know how to get to the actual code for this, right? So who here knows how to find where library dependencies is defined? So what you need to do is you need to go to the sbt/sbt repo, keys.scala, and you have to remember it's keys.scala, it's not any other file. There's one file with not all, but most of the magic in it. And you can grep for library dependencies. Sorry, I misspelled this. And you can see that, okay, now that I've grepped for this magic file, I know that library dependencies declares and manages dependencies. Okay, so at least I have some documentation, not a lot, but some. But what's next, right? What else do you ask? Who's using this? What does it use? Like, what's going on here? You give me a string, you have an identifier, you have a type, but comments and types are not the only things to do with the code base. I want the implementation. And if you start grepping library dependencies, there's nothing. So what do you do next? What you do next is you go to the search bar and just search the entire SBT code base for library dependencies. And, whoops. Yeah, and this is how you figure out what tasks do in SBT. Sorry, let me go back to the... So yeah, you'll start seeing it being used, you'll start seeing it being assigned in various build files and... sorry, I clicked on the wrong thing. Various build files, various Scala files, various test suites and other random things. And from this, you're meant to figure out what library dependencies does, or what library, who's using it, and what it uses, and how it does it. So good luck to you if you end up in this state. So again, for library dependencies, this is generally kind of not really a problem. You know what it does. But that kind of just reinforces the fact that there's a small number of things you know what they do just from the documentation from Google or from Stack Overflow. And for the rest of it, you just hit the wall. There's no way you can figure it out. You go and just grab the entire SBT source code and maybe you'll be able to figure it out. So for MIL, it's different. So here it's called IVDEPS. It's a bit different name, but whatever, it's the same thing. Immediately, I can see that if I open up IVDEPS, I get documentation. So any IV dependencies you want to add to this module in the format of IV or : name : version for Scala, or single : name : version for Java. So that's nice. What else can you do? You can say, you can ask for the super member. So in Mill, the override keyword is optional. I can put it here explicitly if you want to see it, but we make optional for conciseness. But what's interesting is that these Mill tasks, they're not these magic variables that get assigned somewhere and used somewhere else. They are standard Scala defs, and they override other Scala defs. And in this case, I can see that, okay, it comes from Java module IVDEPS. And like any other Scala code, I can see where is IVDEPS being used. Okay, it's used in all IVDEPS. It's used in transitive IVDEPS. Transitive IVDEPS also uses mandatory IVDEPS. Where does that come from? That comes from here. You can override it. It uses the upstream transitive IVDEPS, so it's recursive. As you'd expect, transitively collecting the dependencies is recursive. If I go back to where all IVDEPS was earlier, you can see it pulls up mandatory IVDEPS and IVDEPS. If I find the usages of all IVDEPS, this one is not in a separate file, so it doesn't pull up. But basically, you can see this code is a lot more useful than the code we saw in SBT. So you pull up your keys class file, which is what we saw on the right. You look at what Mill gives you on the left, and hopefully you can understand like this is what you expect from ID support in a large Scala code base. And the right-hand side is not what you expect from ID support in a large Scala code base. So Mill isn't doing any rocket science here, just taking the stuff you already have and applying it to your build tool. So I can jump around, like here I have transitive compile class path. It looks at local compile class path, I can jump to that. Local compile class path uses compile resources, what's that? I can jump to that too. Oh, compile resources is like the Mill source path in the folder compile-resources. So these are some very nice things that you can do in Mill that really helps democratize the build for you. Like you're not stuck when you hit something you don't understand. You can keep digging and digging and digging. And even if you can't find what you want on Stack Overflow or Google, you can probably dig through the code base and figure out what you need to do, and the ID will help you. So back to the slides. That's ID support demo. Let me check time. 15 minutes left. So that's understandability. Last point is extensibility. So most build tools require extensions to be published as plugins. I need to do foo, I need a foo plugin. Bar, I need a bar plugin. The foo plugin is unmaintained, well, I'm kind of stuck. The bar plugin doesn't do what I want, I'm also maybe stuck. So Mill, interestingly, lets you write code or import any library from Maven Central without needing plugins. So there are plugins. Like earlier we saw the Mill ScalaFix plugin was used to get the ScalaFix integration. But in the absence of a plugin, you can often just write code to do things yourself. And we'll see how. So consider this minimal Scala module, even more minimal than the one we had earlier. No dependencies, no test suite, just compile Scala, in this case 2.13.8. You can compile it and it will compile Scala. So a custom task in Mill is just a method, def. So you all know defs. I say def line count equals task. Let's say I depend on all source files. That's something inherited from Scala module. Again, the ID will help you if you don't remember what it's called, what it does. And I map it to the lines, the count of the lines, and I sum them up. That's my line count. So line count is kind of a fake, not very interesting custom task, but just representative of the weird ad hoc things you all need to do in your build. And maybe you need to package up some strange format, deployment container format. Maybe you need to create a bill of materials that's servable from your web server so people can inspect and see what's going on. So there are plugins for some of these things, but often there are all sorts of weird requirements that you need, and plugins may not fit exactly what your business needs for your code base. So with Mill, it's very easy to say, well, here's my line count task. It's a custom task, just one line of code. And I can override my resource task to say, okay, write the line count to a text file and append this folder containing a text file to the super resources. And you all already know what override and super do, so I hope I don't need to explain it. And now, when I call mill foo.run, because I've overridden resources, it's going to use a new version rather than an old version, and I will be able to print out at runtime the line count 17. So line count is maybe a very boring custom task. Let's say you want to do something more interesting, like I want to render a HTML page because I need it statically rendered, because I do it at runtime, it's too slow. I do it at application startup time, it slows down my application startup. I want to do it at build time. So with SBT, you probably won't do that build time. You'll just live with a slow startup or you'll live with a slow application. But with Mill, it's actually very easy to do this stuff. So Mill does not ship with a HTML templating library. It's a build tool. But Mill has this magic import syntax that allows you to just pull in any library you want and use it in your build. In this case, we put in Scala tags over 12.0. I can then import the Scala tags code, and I can then convert my line count into a HTML snippet that just uses Scala tags right there. And let me just show this to you live. So close this. Custom. So over here on the left, I have the line count thing that we saw earlier. You see, I can show line count at print 17. I can say mill foo.run, it'll print line count 17. It's able to fetch the code resource at runtime and print it. I won't show the code. It's straightforward Java code, Scala code. So if I try to import Scala tags.text.all.here, you'll see it's not happy because Mill doesn't ship with Scala tags. But I can import iv comly howie Scala tags ::0.12.0, and then I can just reload my IDE. Mill integration should take a second or two. Okay, now it's done. This spurious warning. And now Scala tags is integrated into my build system. I can jump to it. I can look at the jars on my IntelliJ class path, external libraries, and I can start using it. So let's say I want to call this line count HTML. And we could say div h1 line count, not lint count, line count, p, then I just put this in here, dot render. Again, you can see IntelliJ nicely highlights line count down here needs to be updated as well. It's normal Scala, and IntelliJ, as far as it's concerned, treats it as normal Scala. So I can show line count HTML. It's just a normal task, like any other. Give it a second to recompile my Scala code. Okay, here we are. So you can see my div h1 line count p17 on the bottom left. I can inspect line count HTML. It'll tell me, okay, it's on build.mil line 9. That's what I want. Total number of lines in module source files. That's what I wrote up here. And the inputs are all source files, which is what I wrote here. And if I want to see what all source files does, I can just auto-complete it, all source files, and ask Mill. And okay, all individual source files fed into a Zing compiler. You want to know all source files does? Jump to it, and there's a library method called, find source files and all sources. And you can keep jumping in to figure out, see what's going, what these things do. So back to the slide, like I show this to you working. And again, what's interesting thing here is there is no Scala tags Mill module. There is no Scala tags line count module or plugin. Like we just took in the standard libraries that you already know from Maven Central, Scala libraries, Java libraries. You just pull them into a build and start using them to do the things you need. So even the things you need to do are not the same as the things some guy on GitHub maintaining a plugin needs to do. It doesn't mean you're stuck. It means you can proceed yourself and just get what you need done. So that's what we need. These are 3 reasons for why Mill. The foolproofness, the understandability, and its extensibility. So lastly, let's talk about how Mill works. So at a glance, Mill basically makes you define objects that inherit from classes or traits. And like any other objects and inheriting from classes or traits in Scala, you get methods from these traits. And these methods form a graph, like foo.sources gets used by foo.compile, foo.compile gets used by class path and resources get used by assembly. It forms a graph. And in Mill, this method graph becomes your build graph. So if I override line count, if I add a new method line count here, and I override resources down here, what we saw earlier, the method call graph changes, as we see in the top right, and in the same way, your build task graph also changes. So if I kind of show the sources and assembly down here, just to show you the thing that was actually inherited, you'll see that the graph of the data flow graph through your methods, your sources gets used here, line count gets used here, resources gets used here, is exactly the same as what we have conceptually in your build. And once we have this graph, we can do interesting things with it. For example, we can parallelize it to show that, hey, the blue things up here do not depend on the red things down here, so blue and red can run in parallel on separate threads. The green foo.assembly on the right needs to wait for both blue and red to finish before it can start. So that's kind of simple and straightforward. Mill gives you, automatically caches all your tasks for you. So line count is automatically cached to outfoo linecount.json. Compile is automatically cached to outfoo compile.json with any files in the outfoo compile.destination folder. And yeah, if you want to look at assembly, it's the same pattern. All tasks in Mill are automatically cached with the exact same like file system format. And lastly, Mill can handle invalidation for you. So let's say I add a new file in my resources folder. Well, the resources folder is not my current resource task because that's override, but my super resource task, right? That is one that's being overridden. And Mill has this graph. So Mill can see that, okay, I touched full super resources. I automatically know I need to re-evaluate foo.resources and therefore re-evaluate foo.assembly. So all these things are kind of nice. And these are things that almost all build tools do or try to do. But what's most interesting thing here is on the left, the code we use to configure Mill has nothing to do with parallelism, caching, and validation. You don't see any threads, you don't see any futures, you don't see any cache key computation, you don't see any semaphores, mutexes, file system reads or writes, or serialization code. All that's handled for you by Mill. So all you need to do is you just write your so-called straight line business logic in your build. This is actually usually really simple, right? Like I compute a value based on the source files, I override resources and call super. These are all straightforward business logic. And all the caching and validation, parallelism and stuff is all done for you. So that's kind of a quick lightning summary of how Mill works. I won't go into the details here because there's a lot of depth to it. So this is the last slide, and just to wrap up, Mill is an open source JVM build tool. It supports Java, Scala, Kotlin. It's foolproof. It's quite a lot more understandable than tools like SBT, and it's a lot more easily extensible. And the way it works is that Mill modules are just normal Scala objects, and Mill tasks are just normal Scala methods. So all your normal object and method stuff works. Superclasses, traits, super, override, all those things work just as you'd expect. You already know how they work. I don't need to teach you. And from this module tree and task graph, Mill provides automatic caching, parallelization, validation, and other things that you'd expect from any modern build tool. So the documentation's at millbuild.org. Again, can go check it out. There's, getting started. There's contributing instructions. There's a bunch of bounties there. If anyone wants a few $100s, there's some money on a lot of these tickets. And please try out Mill. Let us know how it goes, and I'll now take questions. I think we have like 5 minutes for questions according to the schedule.
Yes.
Yeah. Okay.
Is the Scala compiler going to use Mill at some point?
We don't currently have any plans for that. So the ones who are using Mill that you'd have heard of is obviously all my projects use Mill. Scala CLI uses Mill. If you use Scala CLI, Corsair uses Mill. If you use SBT or Bazel, those all use Corsair as a dependency resolver. All the Scala hardware design projects seem to use Mill for some reason. So Chisel, Spinal HDL, all those guys like Mill. I don't know why, but they do. So people do use it. Not sure when the compiler will, but hopefully more people, and maybe someday they'll convert over.
Thank you for the presentation. And does Mill contain templates like GitHub?
Mill does contain templates. So if you go to the Mill documentation, let me just pull that up, which I can just click on this link. Go to Mill documentation. Every example here is part of our test suite and downloadable and runnable locally. And if you use the Mill init command from command line, it'll let you choose which example to download if you don't want to use curl. So yeah, templates for the Hello World module, templates for Scala.js, cross-version, cross-platform publishing. I think we have templates for Scala Native now in the latest version. Let's take a look. Yeah, templates for Scala Native, linting testing examples, and this applies to all languages. So we have all the same equivalents for Java as well as Kotlin, and some basic stuff for Android. So you can go to documentation, and anything you're curious about, just click the download link. For example, this download link here, and you'll get an executable project.
Thanks for the talk, first of all. I have a question. It might be incredibly stupid, but just because I've never used Mail. So I assume that the reason you declare dependencies as Ivy depths is because Mail is using Ivy as a dependency solver. Have you ever thought about migrating to CoCL like SBT did a while ago? I think they did it for performance reasons, but I don't know. Have you ever considered it?
Yeah, we actually migrated like 5 years ago, but the name stuck around and we haven't.
Okay. That was a chance. Okay. So that was a stupid question.
So
okay.
we do use Corsair as well, but names have a very sticky nature.
Hello, thank you very much for the talk, and thank you very much for Mail. I wanted to ask about the comparison between performance of SBT and Mail. You showed that the performance of Mail is really comparable with SBT, even if it's comparable with SBT performance.
Yes.
When it's hot, when SBT is hot and it's already run for a while. What enables Mail to achieve this? Is it like an architectural
Mail does the same thing as Gradle does, which is you run it always from the command line, there's no shell, but it'll automatically manage the background long-lived process for you. So if you use Gradle or use the new Maven D, they all do this kind of pattern, and Bazel as well does this. So the first time you run it, it'll inevitably be slow, same as SBT. But after the second, third, fourth time you run it, it speeds up and it's kind of managed for you, so you don't need to open the shell and kind of juggle the shell yourself.
Okay. So it's like it's launching a server
Yes.
in the background and just connecting to it.
That's right.
Okay,
Yeah.
I see. Thank you.
Is Mail using SBT to build?
No.
Do you, no.
Yeah.
So you build Mail with Mail?
Yes.
Okay.
Yeah. I think we've been building Mail with Mail since 2018, so it's not a recent development. It's been bootstrapping for forever, and there are some annoyances in bootstrapping, but generally it works fine. Yeah. Before was SBT. I mean, there was no Mail back then, right? Or it didn't work yet. Yeah. Any other questions? All right. I guess we are done.
Thank you.
Thank you, everyone. I'll save the screen recording.
Yeah, thank you.
Yes.
Non, mais ouais, bon, je dois récupérer en plus.
Okay, please. Just before I leave you with Nicolas, a few words from the organization. So Scala IO comes to an end this edition, and I'm exhausted. Just thank you again to our sponsors that enables this event to happen, and also thank you to EPITA to host the event. I will send an email right after, but there will be a post-conference gathering if you are still in Paris and want to, I don't know, drink beers with people from the conference. It will happen there. And then I should have had a question mark. But yes, we're quite exhausted, and if you want to help us, if you want Scala IO to continue, please reach out, send me a message, talk to me, or send an email to contact@scala.io. Because to be honest, I don't know how long we will be able to continue this with 3-4 orgs. So that's not sad, but yeah, and actually Jonathan is not here. I wanted to ask you for a big round of applause for Jonathan, because basically he does 80% of the work. So that's it. I will leave you with Nicolas. Thank you.
Is this working? Can everybody hear me? Good afternoon, everybody. My name is Nicolas. I am currently employed at JP Morgan, where I work on a lot of very exciting projects that have absolutely nothing to do with what I want to talk to you about today. So I'm just... Can you not hear it? All right, okay. Let's sing that. Can you hear me in the back when I speak like that? All right, okay. So did you not hear anything I just said? It was just about me being called Nicolas. The rest is irrelevant. I am here today because I want to teach you how to write a general-purpose programming language. And I think you should want to learn that first, because I think this is a third talk on the subject in this conference, so clearly it's topical. Second, because it is going to allow you to update your mental model and to have new insights on a tool that you presumably use most of the day, most days, and thus making you a better programmer. You're welcome. And you also should want to learn that because if you can write a general-purpose programming language, you can definitely do the relatively simpler exercise of writing a domain-specific one, which is a bit of a game changer when you have to maintain software whose domain experts are non-technical. It will let them express their rather esoteric and specialized knowledge using their own words directly to the compiler, to the computer, without having to use you as a rather dubious interpreter, translator. Thus allowing you to save a lot of time, but more importantly, to blame them when things go wrong. And the reason you should want to learn that from me is, well, I'm rather good at this, sure, but more importantly, I've had to do this exercise a few times, and I found it so fun that I decided to learn how to go about it properly. Most people would do that the other way around. You'd probably learn how to do the thing and then do the thing. It's way too reasonable and boring for me, so I did it the other way around. In hindsight, it was probably not the best course of action to take. I made all the mistakes. I fell in all of the traps. And therein lies my real talent, falling into traps and disarming them. So I know them all. And so I hope that I'll be able to help you steer clear of the most egregious of these mistakes that one can make. And if you're wondering, yes, I did have to look up how to pronounce egregious before walking on stage. And no, I don't know whether I said it right. Right, so now that the stage is set, what's a programming language? And the way I like to think about it, a programming language is a set of terms and the rules to combine them into concrete and precise expressions that you use to give a computer some instructions. This usually comes under the form of text, which we are going to call code, and you will provide that code as an input to some software to do stuff with. That stuff could be, well, for example, you could take your code and change things around to make it look nicer. We call that a formatter. You could rewrite bits of the code with semantically equivalent but faster bits. We'd call that an optimizer. You could write equivalent code in a different language. That would be a compiler. Or you could simulate the instructions and return the result of executing the program, and we'd call that an interpreter. What we are going to be concerned with today is mostly interpreters. And I've been very careful to phrase that so it's clear that we're talking about functions. All of these things take program code as an input and yield something. In the case of an interpreter, we go from code to the result of running that code. And whenever you're thinking about functions, you have to be quite precise about your domains and your codomains. And in the case of an interpreter, what is code? So that's the first question we're going to ask ourselves. How do we represent code? You might naively think, well, code is text. Text is traditionally represented as strings. So we could use a string. But if you know anything about me and my work, you know I can be a bit of a snob when it comes to types. And there's infinitely many more invalid strings, strings that don't represent legal code, than there are strings that represent, said that the wrong way around, didn't I? Illegal code than represent legal code. So we're going to tighten that a little bit. We're going to come up with a better type to represent source code. Now, source code is still text in the beginning. I am going to completely skip over the part where we go from the text to our representation of source code, which is called parsing. It's a very interesting exercise, but not at all the subject of this talk. It's a 1 hour talk, not a 7 hours one, so we're not going to talk about parsing. Just assume that we know how to parse. So let's get started. This is a bit slow, right. The simplest program that you could ever write is just an integer. That's not very interesting. We're going to go slightly further, not much further to begin with. We are going to be able to add numbers. So we see that this language has two different constructs. We have numbers or addition of numbers. And whenever you want to represent something that is an or, you have to think about sum types. So we're going to try to write a sum type for expression, which has two variants. The first one is going to be numbers, 2 here, so wraps a number. And the second one is going to be addition, which has a left-hand side operand and a right-hand side operand. And that's it. That is the most basic representation we can have for code. And as I said, we are going to try and interpret that code. So we have to think about how interpretation is going to work. And I'm going to try and introduce some formal semantics to describe how that should work. It probably is going to be slightly familiar to some of you, but not entirely, because I've taken existing notation and made it mine and tweaked it because I wanted things to be a bit simpler. So everything I'm going to show you is kind of correct, but not entirely, because I wanted things to be understandable. Right, so we're going to introduce formal semantics. This says that if we encounter a num, it's going to evaluate to something. So what do you think this interprets to? Well, a number, right? The value that's wrapped in the number. That's simple. Then we have to do addition, which has a left-hand side and right-hand side. And what you want to think, what you'd like to do is say, well, this is what is going to evaluate to. The left-hand side plus the right-hand side. But those are expressions, aren't they? They're not numbers, so you can't add them. What you have to do is to say, well, actually, this only works if the left-hand side evaluates to some value v1, and the right-hand side evaluates to some value v2. But in that case, I'm going to... This is interesting. Okay, so on my computer, that bar spanned the entire width of the screen. But this is not my computer, because I had to change for captation reasons. So please pretend that whenever you have one of these horizontal bars, it's just long enough to cover the entire text, because it's supposed to look really nice. So pretend that it looks nice. And that bar separates two parts. Everything that's above the bar is called the premises or the preconditions, and this is the thing, if these things happen to be true, then whatever goes below the conditions or the consequence holds. So whatever goes after is addition evaluates to V1 plus V2. It's not very complicated so far. And that allows us, now that we know exactly what it is we want to implement, we can easily write our interpreter, which goes from an expression to an integer. And since expression is a sum type, well, the only tool, or the best tool at least we have to work with sum types is going to be a pattern match. So you're going to pattern match on it. We have the num case, and we know the solution for that, right? It's just it evaluates to value. And addition, well, I'm going to move that to its own function, because otherwise, by the end of this talk, we're going to have lots of terms, and it's not going to fit on one slide. So addition is, again, we want to make sure that the left-hand side evaluates to V1, the right-hand side to V2, and then we can just add the two. Fairly straightforward. I will be using the words interpret and evaluate interchangeably. That is not correct. I'm so used to call that evaluating that I find it really hard not to use that word. But apparently, you should call that interpret, not evaluate. So please don't quote me on that. I'm wrong, but I can't do anything about it. Right, so let's check that what we've done works. 1 plus 2 is going to be represented as the following expression, add, of num1 and num2. And if you run that, we get 3, which is what we were hoping for. This construct of using a sum type to represent expressions is quite common. It's so common that it's got a name. It's called an abstract syntax tree, which I'm going to be calling an AST from here on out. And AST has two parts, abstract syntax and syntax tree. And it's called abstract syntax because we are working at a level where we ignore a lot of the details of the syntax. For example, here, 1 plus 2 is strictly equivalent to that string over there. But that does not change the abstract syntax tree. Or that string as well. So at the AST level, we get rid of all the noise that you have in the text that people might use to make the code look nicer or to disambiguate operator precedence, for example. So it's abstract because we abstract over the details of the syntax to get what the expression truly means. And it's called a tree because it is a tree. Your root is going to be the operator, and your leaves are going to be the operands, which gives us a tree. Now you might think that's not much of a tree. It's got a depth of 1. It cannot be any deeper nor shallower. It's not very interesting. It's more of a bonsai than a tree, really. And that's actually a problem that we have. Because if we wanted to not do 1 plus 2, but something crazy like 1 plus 2 plus 3, well, we don't have the tools to represent that in our AST, which is a sign that we've made a mistake. Here's a mistake. We don't want addition to have numbers for operands. We want it to have expressions for operands. And then you have a proper tree. And then it can be arbitrarily deep. And that's fine. So now that we fixed that, we need to fix our semantics. We're not working with numbers any longer, but with expressions. And nothing else changes because an expression still interprets to the number for the left-hand side, right-hand side. And, sorry. And so everything still works. I'm really bothered by that horizontal bar, I'm sorry. Right, okay, so now we're going to fix our expression to say what we wanted initially, which is 1 plus 2 plus 3, which evaluates to 6, which is exactly what we wanted. So we have done the very basics. The first thing we need with a language is the most basic way of representing source code. And what we've learned is source code is represented as a recursive sum type. Our expression is a sum type because we have different parents, and it's recursive because it's expressed in terms of itself. It's called an abstract syntax tree, and interpretation is done through pattern matching. This is the basics. This is a base of what we need to know in order to do the rest. But of course, we're not going to stop here because we haven't written a programming language here, have we? We have written a glorified calculator. It's not very useful. So what do we need to add to make that closer to a proper programming language? Well, the first thing is the ability to take decisions. Conditionals, if statements. Where an if statement is composed of a predicate, evaluates to true or false, and then a then branch or an else branch. And let's work on the semantics of that. The way that works, condition then has your predicate, your else branch, and your then branch. I'm calling them on true and on false in order to fit on the slides. And the way you want to evaluate that is predicate needs to evaluate to, well, you want to do something different depending whether it's true or false, don't you? And we don't really have the syntax for that. But we don't need syntax. What we do is we create multiple rules. So we're saying this is what happens in a true case and in a false case. And the way the interpreter is going to work is if it finds any rule like that that matches, then we have a success. If it doesn't find a rule that matches, then we have a runtime error. So in a true case, we're saying that we have to evaluate the untrue branch and return that. In a false case, we are going to evaluate the on-false branch and return that. And those are the semantics of our conditional, which is going to be fairly easy to express. The first thing we need to do is to update the AST to have this variant, where conditional has a predicate on true and on false branches. And the interpretation is again going to be in its own function, cond, where what we do is if the interpretation of pred, the predicate evaluates to true, then we evaluate the untrue branch, otherwise we evaluate the unfalse branch. Can anybody spot the mistake here? I know you can. Thank you. So that is a problem. Interpret returns an int. You cannot use an int in an if statement. Well, you could in some languages. Some languages have something called truthiness, which is obviously an abomination, but we could try to implement that. We could do that. We could try to say, well, we're going to try to pretend that some values look more truthy than falsy. This kind of looks like true. So we're going to say that 0 is false, anything else is true. We could do that, but I absolutely hate that. One of the reasons I hate that is different languages are going to take different decisions. And I remember a while ago, I think it was maybe in Delphi, a very old language, where they had decided that 0 was true and anything else was false. And it took me days to understand why my tests weren't working. So I do not like this implicit convention of we're going to assume that everybody knows what it means and then we get it wrong. So we're not going to do that because we have some self-respect. And what we're going to do instead is realize what we want is interpret, not to just return integers, but to be able to return integers or booleans. We're going to have to start having types in the language. And since I said it's either an integer or a boolean, again, whenever you have something that's one thing or another, you need a sum type, which I'm going to call value, which has a num branch for numbers and a bool branch for booleans. And then interpret can return a value. We need to update our semantics, obviously. Num doesn't return a value, but wraps it in a number. Similarly, addition, well, we don't want any v1 and v2. Now we need to check those are numbers. And if they are numbers, then we need to wrap the result, the addition, in a number. That's going to force us to update the way this has been interpreted, because now we might fail here. There are scenarios in which this doesn't work. If any of the values is a Boolean, then it doesn't work. So let's rewrite this whole thing with this rather complex bit of code, which tells us the left-hand side must be a value, a num, so the right-hand side must be a num. And if that matches, then we can just return their addition. Any other scenario, however, is a type error, which happens at runtime, which bothers me a little, but still a type error. And now we have all the tools to write the conditionals, because we said that the predicate must evaluate to a Boolean, and the rest doesn't change. Any v works, we can just return that v, and that's going to depend on the type that we had. So this now becomes a lot nicer, because it matches our formal semantics quite closely. If the interpreter, if the predicate evaluates to true, then we return the untrue branch. If it evaluates to false, then we return the unfalse branch. And if it evaluates to anything, then we have a type error again. We would like to try to check whether what we just wrote works. But of course, we can't really, because we don't know how to introduce Booleans to our expressions. We support them while interpreting them, but we don't have a way of writing one. So we're just quickly going to need to add a new terminal language, Booleans, which take a value and just returns a value.bool. That's going to force us to update our AST, Boolean, which wraps a value, and the interpreter is fairly straightforward. You just return that value. And now we can check whether this works. That's going to be a cond where the predicate is true here. The untrue is 1, and the all false 2. And if you run that, you get num of 1, which is exactly what we wanted. So we have added successfully conditionals to our language. The key takeaways, what we have learned so far, and that you need to remember, are, well, conditionals are actually fairly straightforward to support, but they have forced us to support multiple types of values. Now we have to support Booleans and integers. And eventually we could support many more types. Of course, here, this is sufficient for what we want to see. And yeah, don't do truthiness. It's just, nah. Next thing we're going to want to do is the ability to name things. It's something that you do quite a lot in programming languages. You declare variables. I'm not going to call them variables here, because variables, well, it has the subtext of mutability, doesn't it? Something that can vary. And while I don't think mutability is inherently bad, and Scala has mutability, so clearly it must not be all bad, it's a decision that's very important to our language, so I want to postpone the moment where we're actually going to add that to the language as much as possible. So I'm going to just call that let, because var sounds like it can be mutated, val sounds like it cannot. I do not want to make people feel one way or the other, so let works quite well. And you should be pretty clear what this evaluates to, right? We're saying that some x is bound to 1. This should evaluate to 1. That's pretty clear, right? Yeah. This should bother you a little bit more. What does this evaluate to? Well, it depends. In some languages, that's going to evaluate to null. Some languages to 1. Some languages are not going to accept that and refuse to run it. Some are going to run it and fail. It's just, you have to decide that on a per language basis, but the importance of that is it shows you, and you should feel it just by looking at that. This X binding, this X let statement is only valid on some subset of your code. And that subset is called the scope of the variable. And we have to decide how the scope works. So we're going to do the simplest possible thing. We're going to make that part of our syntax. We're going to say that the scope works on everything that's after the in keyword. Right? And the way we're going to evaluate that is by saying, well, whenever we encounter that, we're going to move the knowledge that x is equal to 1 upstairs, which I'm going to call the environment. So we know that x is equal to 1, and that binding is legal here, in the body of the let statement. We know what x is bound to. It's bound to 1, so we can substitute that with the value that it has, and then just reduce the rest to eventually get to 3. Now, there's a few tricks here. This seems trivial. The intuition that we have for let statement works. But what about that one? What are we going to do here? Do we want to compute 1 plus 2 before storing it in the environment or after? Are we going to store the value, 3, here, or the expression 1 plus 2? It's quite an important decision to take. You might say, well, Shreeze doesn't change much. It's still going to evaluate to the same thing, isn't it? And yeah, it is. But it might have, it does in a pure language. Most languages are not. But also, it might have quite a big impact on performances. Here, for example, if I were to compute 1 plus 2 before doing the binding, then I would evaluate the predicate, realize it's always true, so I'm always going to run 1. I never needed to evaluate x in the first place, and if it was a very consuming operation to run, not 1 plus 2, which is basically immediate, but then I would waste a lot of time computing a value that I never needed in the first place. So you would say, well, clearly then we do not want to evaluate first. We want to store the expression in the environment. But in some other circumstances, that's actually going to be much slower than the alternative. So there's no good decision. There's not one way of doing it that's clearly better than the other. There is one way that is, at least to me, more intuitive than the other, which is to store the result of computing the value in memory, which is going to be called eager evaluation as opposed to lazy evaluation. So, the way we're going to interpret that is by computing the value of the lead binding, moving that in the environment, and then doing the substitution until we get the result that we want. So that already tells us we have made an important choice here. We have decided to write an eager language. Now, what about that? It's pretty clear what should happen here, isn't it? X is 1. So this is really telling us 1 plus X is 2 here. That's really 1 plus 2. That should evaluate to 3. That's pretty clear. I hope everybody agrees that this should evaluate to 3. Now, what if I were to swap the operands? That's an addition. Addition is commutative, isn't it? So clearly, that should not change the result. But, well, we have to think about that a little. Because if we were to run that, we're saying X is bound to 1. So we move that to the environment. X is bound to 2. So we should move that to the environment, right? X is now bound to 2. And if X is bound to 2, then we're doing 2. The entire let statement is replaced with 2. Plus X, which is equal to 2, and we get 4, which is not at all what we wanted to get. So we have a bug here when we implement it naively. Because this ultimately evaluates to 4, there we go. And the bug that we have is we have implemented something that is really very bad, which is called dynamic scoping, which lots of languages have implemented in the past. Every once in a while, a new language is going to say, oh, that's actually not such a bad idea. It's so much easier to implement. Python did that a while ago. It took them quite a while to get rid of it. It's an unarguably bad thing to implement. The right thing to implement is to consider that that each variable that you declare doesn't replace the old value, but goes on top of it, like if you were to push something on a stack, say. And that stack frame is only valid in the body of the let statement. So here we would see that X is equal to 2. We just look for the first binding that matches. So X would be equal to 2, which would allow us to replace this statement with 2. And then once that let statement is finished, we get rid of the stack frame. So now X is equal to 1, and we can do the normal reduction and get the result that we wanted, which is 3. The act of declaring a variable of the same name is called shadowing, and it's a pretty important property to have. It's called lexical scoping. Static scoping, lexical scoping, I think it's both. And the reason it's called static scoping is because by looking at your code, you can know exactly which value a name is going to be bound to, whereas with dynamic scoping, it depends on who spoke last. So you can't know, you have to run the program to know how the binding works. Since you have to run the program, that means dynamic. Right. Now that we have a good idea of how we want our let binding or variables really to work, let's formalize that. Let has a name, a value, and a body in which the value is bound to the name. And the way it's going to work, well, we want to interpret the value. That's the first thing we want to know. And the second is we are going to want to evaluate the body, but not that simply. We want to evaluate the body knowing that name is bound to value. Having an environment in which name is bound to value, which is, we don't have a notion of environment yet, so we're going to have to add one. That new syntax that I just introduced is telling us in environment E, value evaluates to V1. And now we want body to evaluate to some V2 in an environment. That environment, well, it's going to be E, but in which name has been bound to V1, the binding part. And once we've done all that, then the entire let statement evaluates to V2. Pretty straightforward. Okay, and we also need, once we encounter a variable, X here, to be able to look up its value in the environment. And that's, the semantics of that is just, well, it's got a name, and the semantic is just look the name up in the environment. So, we now have two new statements, let and ref, which we need to add to our AST. Let has a name, a value, and a body. And ref has a name. And of course, the two names need to match. That's how it works. And if we want to start interpreting it, we are going to need to code that environment. So let's do that quickly, it's not very hard. An environment, as we said, is a stack, which in Scala is represented as a list of bindings, where a binding is a name associated with a value. We want to be able to look up a name in the environment, so that's just going to be find the name, find the first value that has that name, return the value, or fail. We need to be able to create a new binding, which is, well, create a new binding, push it on top of the stack, and wrap the entire thing in a new environment. And of course, just out of courtesy, I'm going to use to create a helper that allows us to create an empty environment. Now that we have the notional environment, we need to pass it everywhere. I'm not going to update all the code, pretend that all the other functions have been updated with the environment, because it's really boring to do, and I don't want to inflict that on you. And we can do let, which is going to work that way. First interpret value, interpret v2 in an environment where we have created the binding, and then the value is just, the return value is just v2. So interpretation is fairly straightforward. And reference is quite easy. You just call lookup, and that's all there is to it. Well, let's check how that works. If you remember, that's the example that I used before. That was supposed to return 3, but returned 4 if we did naively. But if you do, yeah, the AST is starting to be quite big, so I'm just going to show you ellipsis. You just have to trust me that what we're running is actually what's written on top, and that evaluates to 3 as we wanted, not to 4. So what we've done then, we've learned that local bindings have a scope that can be analyzed statically, very important. We know that local binding can be shadowed, but they cannot be overwritten. And that their interpretation requires an environment which we just had to code up. Right, okay. One of the last aspects that we need in a programming language is the ability to reuse code. What I mean by that is, this is a little, well, I find that a little disappointing, because we're saying, for any x, I can compute x plus 2. Any x at all. But I'm only ever going to do it with x equal to 1. And that seems somewhat less than useful. It could be much more powerful. We could say, well, for any x, and then you pass me whatever x you want. Really what we want is to replace that with this, where we're saying, here's a function that for any x maps it to x plus 2, sorry. And then we are going to apply that here to 1, but we could apply it to anything. Really what we want is functions. And the way functions are going to work, the intuition on how we're going to interpret them, to evaluate them, is we are going to replace an entire function application with the body of the function while storing the value of its argument in the environment. So in the environment, we know that we're applying it for x equal to 1, and the entire function has been replaced with this body x plus 2, which is straightforward to evaluate, and we get 3. You might say that this was, sorry, it was a bit fast. You might say this might be slightly less than useful because you've declared a function and applied it immediately, but what I really like to be able to do is to name a function and be able to reuse it in the entire code. And that would be a good point, but we just spent 10 minutes figuring out how to name things. It's just a name statement, isn't it? A let statement, isn't it? We could bind f to the function. We could bind the function x that maps x to x plus 2 to the function f, and then apply it later in the body, in the scope of the variable. Now, this seems very straightforward, but it does mean that we've taken a rather important decision. See, the thing is, let binding binds a name to a value. And here we're binding the name f to a function. Functions must be values. That's quite an important thing to have decided. So we're going to need to update our value ADT to have a function, where a function has got a parameter, x here, and a body, the expression of the body, the body of the function. So that seems well and all, but let's look at this bit of code. So in theory, instinctively, what you were doing here is saying, well, bind y to 1. So really this is just saying the function f maps x to x plus 1. And when you apply that to 3, that should yield 4, right? Well, if we run it naively, let y equal 1. So we got to store that y is equal to 1. We have to store what f is equal to. And then we have y equal to 2. So it's a new stack frame. We have y equal to 2. We don't override the old y. But still, when we apply f, well, the first value of y that matches is going to be 2. Yeah, I went ahead of myself a little bit. Have to do the replacement. There we go, 3. And then the value we have for y is 2, which is not the value we wanted to have, because that means then we get 5. And then when we unpop everything, we get a final result of 5. And we said we wanted to get 4. So we've made a mistake here. And that's quite a subtle mistake to make. That's one of the many, many mistakes I made while writing my languages. The error is here. Y is bound to 1. And we expect y to be equal to 1 here. So what we're really saying is that when we declare a function, we must capture the environment because it's going to be applied. We're going to disregard this assignment here. When we apply the function is going to be applied in the environment in which it's been declared. Another way of saying that is a function closes over the environment in which it was declared. I don't know why it's called closing over. I've read different reasons for that. I never truly got them, but it's a word that we use, which is why sometimes we call these things closures. The function needs to be updated to capture the environment in which it was defined. The formal rules for interpreting functions. When we see a function that has a parameter, a body, well, we're just going to create a new value, a functional value, which has a parameter as a body and the environment in which it was declared. Application is a little bit more fun. So we have a function, and we have the argument of the function. And what we're going to want to do is to evaluate the function, but it cannot be just anything. It has to be some form of function. It cannot be an int, it cannot be a Boolean. And then we have to evaluate the argument of the function, which gives us v1. And finally, we have to apply the body of the function. And here's a tricky bit. We have to make sure we evaluate it in the right environment, which is going to be, well, e prime being the definition environment, but not just v prime. It's got to be v prime in which we have bound param to v1. This is how the body of the function knows what the value of its parameter is. So having done all that, then the return value is trivial, it's just v2. Right? So that would be function application. We are going to need to update our AST to support this. So function has got a parameter, a body, and apply has got a function and an argument. Interpretation is fairly straightforward. Function is just declaring returning of a functional value. And interpretation of application is going to be done in its own function, where we want to interpret the fun as a function. And if that's the case, then we merely have to interpret the argument and then interpret the body of the function in the right environment. Then we can just return v2. And if fun doesn't happen to be a function, then we, again, have a type a runtime. Let's try to see whether what we wrote works. Let of that entire mess, just going to trust me, and that evaluates to 4 exactly as we wanted. So we have implemented functions properly. And you might say, well, that's a little bit boring. Function with a single parameter, that's not super useful. We could not, for example, write an add function that takes 2 parameters. But we could. It's just a matter of shifting your perspective. You could decide that add is a function that takes some x and then returns a function that takes some y and applies and adds the 2, which is called clarification. And we don't even have to change the syntax of the apply call. Add 1, 2 is exactly what happens. So that is going to, again, evaluate to some expression which yields true, exactly what we wanted. So we have functions that take any number of parameters. Scala has functions that take 22 parameters, I think, or with that limit lifted. Our language has any number, which is nice. What we've learned that functions are values. We have learned that they close over the environment. And we have learned that unary functions was sufficient. One thing that we still lack in order to have a proper programming language is the ability to repeat statements. What you probably know as a for loop, for example, or a while loop, We don't have these, and we're going to have to implement them. So the first thing I'm going to do is show you how to implement the sum of all the numbers in a given range with a for loop. Sum for takes the lower and upper boundaries. And the way that works is we have an accumulator initialized to 0. We iterate over the range, incrementing the accumulator as we go, and return the accumulator. I do not like that at all. 2 reasons. Well, the first one is heavily mutable. We rely on the fact that we can mutate the accumulator. I do not want to have mutability until I don't have a choice. So we could try to see whether we have a choice here. The second is really very limited. It only works if we know the number of times we want to repeat the same action. And sometimes we don't. Sometimes we have a queue whose length we don't know and we just want to consume the whole of it, for example. Sometimes we don't know how many times we want to repeat the action. For that, we have a different kind of loop, while. And the good thing is, there's a very mechanical way of turning any for loop into a while loop, which works like that. This is telling us, well, create a value called I, initialize it to lower, and then when you iterate over it, just increment it by 1 every single time. Well, we could do that manually. Create a variable I, initialize to lower, and then each iteration incremented by 1. And then a for becomes a while. So we can go from for loops to while loops mechanically, which is a good news, because that means we don't need to support for loops in our language. We might support it at the syntax layer, but your parser might see a for and mechanically transform it into a while, and when you interpret it, you don't have to worry about for, because having while is enough. While still heavily relies on mutability, because we are changing the accumulator and the iterating value. So the next step is to realize that this really can be replaced with a recursive function. See, these variables are mutated on every iteration. What we could do is we could say an iteration is a function. We don't mutate these variables, we pass new values to a function that calls itself. So you could say, we don't have an accumulator and an I, they're arguments of this function, which are initialized to 0 for I and lower for the accumulator, 0 the way around. And this is telling us that while we haven't reached upper, then we should keep recursing while incrementing the values, which is done easily enough like that. And then this is telling us, once you're done, return the accumulator, which is like that. And that is nice, because we've just shown that, well, I haven't proved it, but I've given you the intuition. Any while loop can be turned into a recursive function call. So since we can turn any for loop into a while loop, and we can turn any while loop into a recursive function call, that means that we have recursive functions, we can support for and while for free. And since this does not rely at all on mutability, it's, at least for the moment, a better implementation because it does not force us to support mutability in the language until we really need to. So, well, the first thing I'm going to do is I'm going to rewrite that properly, because now that we know we want to do recursion, we can do it in a nicer way. Some can be expressed as, well, I really like this way of solving problems. You declare the problems, and that happens to be the solution to the problem. Where we're saying here, well, if the range though is empty, then you have to return 0. And if the range is non-empty, then the solution is the head of the range plus the added to the sum of the rest, which would be the solution to a problem. And now we want to be able to express that in our language. You might feel, well, we have everything we need, don't we? It's just function application. Well, that's one thing we don't have, unfortunately, that bit. So I'm going to declare it really quickly because it's nothing new, but we need it. So we're going to need to have a way of comparing two numbers, gt, which has a left-hand side and a right-hand side. We want the left-hand side to be a number, the right-hand side to be a number, and then we're just going to return their comparison, which means we need to have a new variant in our expression, which has a left-hand side and a right-hand side. And the interpretation is going to be very similar to add, because we are just going to want the left-hand side to evaluate to a number, the right-hand side to a number. And then if that's true, then we can just return their comparison. Otherwise, we have to fail with a type error. So having that, we should be able to express that in our language, which we can, but it's just way too big. So we can. We have all the tools we need. We have let, we have conditionals, we have all the tools we need, but when we run it, we get unbound variable sum, which makes sense. Sum is defined here. We're saying we're going to bind sum to the result of evaluating whatever's on the right. So by definition, whatever's on the right does not know about the name son yet. And yet it's, and that and then but is using it. We have an issue. Let, with the semantics that we have given it, does not allow us to do recursive functions. So we're going to do a new statement. We're going to call it letrec. And the way that's going to work is a little bit unpleasant, but we have to realize that this is going to declare a function. When you declare a function, you capture its environment, but you don't use it. It's only ever used when you apply that function. So we have a window of opportunity here. We have an environment that's not going to be used yet, so we could put a dummy value in there, and once we know what we should actually put in there before application, then we swap that. So there's going to be some amount of mutability. In the interpreter, though, not in the language. That is very important. So when we do that, then the semantics. Letrec has a name, a value, and a body. And we are going to evaluate the value, not in that environment, though. As I said, we want to bind name to some dummy value. Any value, we don't care. Null, probably. And we want to evaluate our value in E prime, that new environment that we've just defined, which allows us to evaluate the body. But again, we don't want to evaluate in E prime as it is. We want to be able to evaluate in E prime in which we have updated name to the proper value, because now we know what the value evaluated to. We have done that on the line just above, which gives us a very solution to the evaluation. Okay, so having that, letrec looks a lot like let. It's got the same parameters. And the implementation, sorry, we're going to need to write this update primitive for our environment, which is going to mutate the environment. Doing this, we want to be able to update a value bound to a name. So the way we do that is by finding that name, updating the associated value. But in order to do that, we must make binding mutables. But again, it's important to realize, I keep saying I don't want mutability in the language, not yet at least. But this is not in the language. We need mutability in the interpreter, but we don't have any mutable primitive in the language. It's still a fully immutable language so far. With that environment updated, we can write letrec, and it's actually a lot easier than it sounds once we have the formal semantics, because it's just going to be following the semantics, create a new environment with a name bound to nil, interpret it, update the environment, evaluate the body, and return the result. It's exactly the code transformation of the formal semantics that we had. And we're going to test it here. Again, too big. It's going to be called letrec, not let. And when we evaluate the whole thing, we get 55, which is a sum of numbers from 1 to 10. So that works. We have all the basic tools we need in the language in order to be able to express all the things that we want. With these primitives, we can express everything. Not necessarily in a comfortable way. I'm not showing you how to do all the nifty things that we can have in a language, just the basics, the core that you need to be able to express every other thing that you can think of. There's one thing that I really dislike about what we've done is, we have realized that loops are implemented as recursive functions. Recursive function need a special syntax and a mutable environment. But again, mutable environment, not mutable language. Now, the last thing I dislike about what we've done, it's completely possible to write nonsensical programs. And we can't find out about them before running them, which I don't like. See, you could write that. You could say, we want to add a number and a Boolean. And that doesn't make sense. And we should be able to look at that and say, that doesn't make sense. You're not supposed to write that. But we don't have the tools to do that. The only thing we can do is run it and realize we have a type error. It would be so much nicer to be able to identify these type errors before we run the code. Well, the first step to doing that is to write a type checker, a function that, given an expression, is, I don't know why I'm looking at my watch. I don't actually know when I'm supposed to stop. How much time do I have left? 20 minutes? We'll be fine. A type checker, well, what do we want the type checker to return, right? Naively, we could say a type checker is going to tell us whether an expression type checks or not. Type checks or not, that sounds like a Boolean. Clearly not the right implementation, but we're going to find that out very quickly. Then our type checker is going to be a pattern match on our expressions. Well, a number is always going to type check. A number is always going to be a number, so it's always going to type check. So that's not a problem. Booleans are also always going to type check. Addition, however, is a little bit more complicated. We have a left-hand side and a right-hand side. So, well, what could we do here? Well, we want them to type check, right? So the left-hand side must type check, and so must the right-hand side. Can you see the mistake here? Because that's lovely and all, but what we had before, if we, rather than interpreting it, type checked it, would still type check. This is exactly what we wanted to not have. So what we have done is not good enough yet. See, the problem here is, yes, the left-hand side must type check. Yes, the right-hand side must type check. But we have an additional constraint on them. We said we wanted both of them to be numbers. And we don't check that here. So we need some way of knowing, when I'm type checking an expression, what was the type of that expression so that I can do further checks later. Which means, since I must know the type of an expression, I must declare a type, which is going to be numbers or booleans, because that's what we've seen so far. And we want the return of the type checker to be something that encodes the possibility of failure. So either of a string, which is going to be an error message, or a type. And, well, now we are going to do a different kind of formal semantics, inference rules, in which we are going to describe what are legal typing rules. So numbers, always, this is read when we encounter a num, is going to type check as, and that's always going to type check as a number. As we said, a number is always a number. There's no question here. So we know this is going to be a right of num. Similarly, for booleans, a boolean is always going to type check to a boolean. So we can write that, and add is a little more interesting. So the rules for add are, we want the left-hand side to be a number, the right-hand side to be a number, separate the two with that messed up horizontal line, and say if everything that's on top checks out, then we can conclude that this checks out to number, this type checks to number. And if the left-hand side or right-hand side evaluate to anything else, type check to anything else, then I don't know what type is add, so we're going to fail. So we're just describing the valid types, type inference that we have. Right, so now we're going to rewrite add in a way that is easier to read. We want to make sure that the left-hand side is a number. This is something that's going to come up a lot. We want to make sure that an expression has a given type. So we're going to write a helper for that. We're going to call it expect, and we're saying that we expect an expression to have a given type. And the way this works is by type checking the expression, and if that's a success, looking into what type we have observed, make sure that it matches the type we expected. And if that's the case, just say, yeah, that's a success, no problem. Otherwise, fail with an error message. And so with that expect tool now, we can just write checkadd in a really straightforward way. We can say, we expect the left-hand side to be a number, the right-hand side to be a number, and if that checks out, then we have a number, because addition adds two numbers to yield a number. And now we're going to write type rules for all of the terms of our language. So, greater than. It's very similar, right? We want the left-hand side and the right-hand side to both be numbers. And if that holds, then greater than is going to type check to a Boolean. So the interpretation is going to be, again, fairly straightforward. We're going to expect the left-hand side to be a number, the right-hand side to be a number, which gives us a Boolean. Things get a little more interesting with conditionals. So we know that the predicate must be a Boolean. There's no choice here. On true, however, could be anything. Some x. I don't care what x is, just that it exists. What about the on false branch, though? Well, we could say it type checks to some y, but then we have to somehow make sure that x and y make sense. We could say it's an x or a y, do a weird Scala-free union type thing. It's complicated. I don't want to do that. So what we're going to do is we're going to take the easy way out and say, well, the on-true branch and on-false branch must have the same type. That makes things easy, and it's reasonable, right? If if both of them evaluate to the same type, then you know exactly what is the type of your conditional. It's going to be that type X. So it's straightforward. We can easily implement it with a checkCon function, where we're going to say, well, we expect the predicate to be a Boolean. And then we want to know the type of untrue, and we expect the unfalse to have the same type. And if all that matches, then we type check to X. Again, a very clear correlation between the rule that we have written and the code that we have written. That would be the conditionals. Let bindings, well, things get a little tricky here. Value has some type X, right? The body has some type Y, but it must have some type Y in an environment in which a variable has been defined. And in the context of type checking, variable being defined just means we know its type. So we want it in an environment where name has type X, and we don't have an environment notion yet. So we're going to have to support it. We're going to have to say gamma here. So in that environment, in the environment gamma, value type checks to X. Is that the case? Then we want to be able to say that we want to be able to update gamma to have some binding. We want to say that gamma in which name is bound to X. And then the return value is clearly just Y, the evaluation of the body. Which, right, now that we have that, we need to do the consumption of a let binding. We need to do this reference. And that's going to be easy. We're just going to look up what time name is bound to in gamma. Which means we have to implement these two things. We have to implement gamma. We have to implement a typed environment. It's going to be very similar to what we did for values. A type environment is just a stack of types, of bindings, where a binding binds a name to a type. And then we need to be able to look a binding up, which is just done by iterating through the stack until we find the right name and then return that type, otherwise fail. Now we fail to a left, because we're doing something clear now. We don't want a runtime exception any longer. We want a value that describes the error. And binding, again, we create a new binding, const it on top of the stack, and return an updated environment. And again, the empty environment, just because we're not root. Type checking then. Type checking needs a typed environment. I have updated all the functions to have the typed environment, and we can just go for let, which is, now that we have the environment, not very hard. We just follow what we said. We want value to evaluate to some type X. We want to type check body in an environment in which name is bound to X. And then if that all checks out, then we know the type, that's why. Reference is simply looking the name up in the environment. And finally, we're starting to get to the slightly hairy bits, functions and recursive functions. So functions. Well, body must evaluate to something in some environment. But that environment is an environment in which param was bound to some type X, right? That's how functions work. And if that's the case, then if the body evaluates to Y, then this all evaluates to the function from X to Y. But the problem that we have, where does that X come from? See, before it was easy. Before we were type checking an expression that was giving us the X, the type that we wanted. But here, we need to set a value to name to a type before we execute anything. So we have a problem here. We can't have that information. We could write a type infra. I'm not going to do that, because that's a lot of work and I don't have the time. So we are going to have to decide that the fact that we want to check types statically has an impact on the syntax of a language, because now we must ask our coders to give us what that type is equal to. We want to have that. We want to know the type of X. Once you know the type of X, then you can set that in the environment and everything works out. So we then need to do apply, application of a function, which, well, this one is straightforward. We have a function, X to Y. The argument must evaluate to X, because the function consumes an X. And if you apply a function from X to Y to an X, then you get a Y. This is very straightforward. Okay, so we said we wanted to know the type of the parameter, so we need to update the AST to have that information. And we can write, well, we're going to need to have a type of functions, because, well, we're manipulating function types now. So we're going to need to have fun, which goes from one type to another type. And then I'm going to do a bit of Scala boilerplate. The boilerplate itself is not super interesting, but I want to be able to write that. I want to be able to write type num to type bool, and for that to mean the function from type num to type bool. And I'm also going to write a quick extractor, because I want to be able to use that in a pattern match, and for that bit to put the from in the X and the to in the Y. implementation details. I just put them here for the sake of completion. Right, so type checking a function. Well, type checking a function, if we just follow the rules, we're saying we want the body to type check to some y in an environment in which param is bound to its type. And then the result is simply the function from x to y. An application is going to be, well, that one is going to be a bit more interesting. In application, we say that we want the function to be a function from x to y. Then we want the argument to be some x. And if both these things hold, then the type is going to be y. If you apply an x to y to an x, you get a y. Anything else, however, is an error. Reasonable, right? And finally, let rec, recursive function. That's the last thing that we have in our language. Let rec, well, we want the value to evaluate to some x in an environment, and that's a tricky bit. It's recursive, so we must already know the type of an expression we haven't evaluated yet. We cannot possibly know that type. So we're going to have to ask the coder to give us x. And then the body is going to be evaluated to type check to some other type in the right environment, which gives us y as a result. Of course, we're going to need to update RST so that value declares its name. The code is fairly simple to change, and we can write our type checker. I was really trying to get everything to fit and align nicely, but sorry. And so type checking let rec is a lot easier than it was to reason about, because now we just know that we want to bind name to x, expect the right types, type check the right things, and eventually you get the right type. So what we've learned, oh, sorry. No, we haven't learned it yet. We must check it first. First, 1 plus 2, the thing that kept type checking before and annoyed us, doesn't type check any longer. And now that let rec, the whole something, the thing that failed before because it failed with a unbound variable error, now fully type checks to a number, which is correct. When you apply a function from number to number to number to number to number, you get a number. So we have the whole thing working. We know how to interpret recursive function, all the things that you need to get there, and we know how to type check them. What we've learned then is type checking is very similar to interpretation, and the way you reason about it is you formalize it, and once you have formalized the whole thing, it's very easy to write the corresponding implementation. We are still allowing illegal programs. So, as you've seen, we are checking whether a program is valid, but we can still build invalid ones. I'm not going to talk about that because it's really very complicated. I have the code, but I'm not going to show it to you because it's dreadful. We could write, the solution would be to write a typed AST, so really a JDT, where each expression is indexed by the type it will return when evaluated. Now, it's super fun to write that. I encourage you to try and do it. It's quite complicated because you have to manipulate type equalities in a way that Scala doesn't make super comfortable. But it's well fun, so I encourage you to try it. In closing, if you only remember just one slide, programs are represented as ASTs. That's one important thing to remember. Second one is we use formal semantics to reason about them. And once we have these formal semantics, then implementation is then relatively straightforward. Because as we've seen, whenever we took the trouble of finding all the edge cases and formalizing the solution, then writing the code was just looking at the formalization and turning that into code. Now, I have given you all the tools you need to start writing programming languages. You don't have all the tools you need to write a great programming language, but you can get a start. And before imposter syndrome kicks in and you start thinking, well, if I try to write a programming language, it's bound to be the worst programming language in existence. Just like to take this opportunity to remind you that Golang is a thing that exists. So go forth, create wonderful, weird, delightful little programming languages, and please share those with us, because it's a really fun exercise. Now, before I conclude, oh, right. There was supposed to be an additional slide, because those of you who attended the keynote yesterday heard Valentin talk about his mentorship program that he wanted to get started. He sent me a link to update my slides with so that you could go and register if you wanted as a mentor. So it's a bit.ly link to Scala_mentor, which I was supposed to add on the slides. I have, but this is not my laptop, so those are not the last version of the slides. Maybe Scala IO can tweet it later?
Yes, send it in an email. And
Please do. Yeah, so that Valentin is not upset with me for not having done. I have done it, Valentin. It's just this is not my laptop. And if you have any question, now is the right time. No, not him. Not him. Nope. No.
Thank you very much. It was a very great presentation. I learned a lot, and I was very impressed by your syntactic choice. And I will know if you can recommend a mainstream language that has a close syntax of the one that you describe here.
Well, that's a pretty quick question. So yes, the syntax highlighter I chose for all that was OCaml. This is very much OCaml because I like the syntax of OCaml.
Nice. Thank you very much.
You're very welcome. I thought you'd like that one.
I'd like to ask two questions. You can answer them in either order. You mentioned syntax sugar, but you didn't give an example of one. Could you have implemented let as syntax sugar around function application? That's the first question. The second
I think I've done that.
Second question is, can your functions actually return functions?
I think I've shown code for both of these things. So let's see. Right, so this would be the code for type expression. Please don't look at it in shortcut. So you said syntactic sugar, right? So functions.
Right. Could you have implemented let as an application of a function?
So here, right? This is let statement, and this is the equivalent function application.
Right.
Right. So I think this is called let apply LLA. I don't remember the name, where any let statement can be replaced by another one where the body of the statement is a function, and the name and variable is just the parameter to the function.
Right,
so here, let is implemented as a function.
So I understand that it's theoretically supposed to be, but in your implementation, you implemented let in your your keywords, and did you make an accidental dependency that you didn't really want to?
I don't need the let statement. I could have gotten rid of that and implemented it in terms of the function. I don't have a parser though. I would do that as a parser level, right? If I find a let statement, I would create a function application immediately. But I also wanted to create some let statement to show you how they work. And the syntax for doing that as an AST is absolutely unreadable. So the reason I have not gotten rid of let and replaced it with function application is just because it looks nicer on the slides. But I could definitely have done that, absolutely. And that would be an example of syntactic sugar. But the other example of syntactic sugar that I gave was, I don't want for loops. I don't want while loops, and I don't need them. I can have them in the syntax so long as they turn into recursive function call. So that would be an example of syntactic sugar, turning for into recursive function calls. Does that answer your question? Perfect.
The second one was whether your functions can return functions.
Oh yes, yes I can. Not my laptop. If we go and see, the add function that I had, it's going to take a while to get there. So the add function, this one, that's a function that returns a function. Add is a function that takes an x and returns a function that takes a while and returns the addition of x and y. So we do have, didn't make it clear, but yes, that's a function that returns a function. Any other questions? Guess not. Well, in that case, thank you very much for coming. I hope you had a brilliant Scala IO. And if you enjoyed it and have the time, please chat with the Scala IO organizers. They need help if we want to have another of these conferences again. And I love them personally. So please, if you have the time, go and help the Scala IO organizers who have done a wonderful job. There was just 3 people to do these entire 2 days. So congratulations.
Valentin helped us with the speakers communication, but there's a lot of things to do on some quite basic things. So everybody can contribute.
Thank you very much.